the Fermi paradox actually has a definitive answer. It is not merely another theory, nor is it just a possibility. It is a conclusion that stands firm when you analyse the mathematics, when you scrutinise the hard data, and when you relentlessly follow the logic to its inevitable end. Most specialists who have dedicated their professional lives to this problem are fully aware of what this answer is. A few are willing to speak it aloud. The majority will not. Not because the conclusion is flawed, but because of its terrifying implications. It reveals something very specific about humanity, about our present era, and the precise technological moment we're navigating. Currently, there are approximately 30 serious hypotheses explaining why the cosmos remains silent. We're going to examine all of them. We will start with the comforting scenarios, then move to those that are far more difficult to dismiss, and finally, look at the explanations that force most people to stop reading before they reach the conclusion. By the end of this analysis, only one explanation remains standing, the one that absolutely nobody wants to be true. To comprehend why that answer is so deeply unsettling, you must first grasp the underlying question, the authentic question, stripped of its poetic interpretations, the one a physicist named Enrico Fermi posed over lunch in 1950 and found impossible to ignore. Picture Los Alamos in the summer of 1950. Several physicists were gathered for lunch. The topic of flying saucers arose. They were sensationalizing newspapers all across the country that week, and the conversation drifted as casual talk does. Enrico Fermi sat and listened for a time. Then, somewhere between eating and the idle chatter, he casually asked, "But where is everybody?" Initially, his colleagues laughed, but as they mentally processed the query, a hush fell over the table. The question sounds deceptively simple, like something you might ask a child who has never contemplated astronomy. But when you truly confront it, when you place the mathematical reality beside it, it evolves into an obsession that doesn't let go. Here is that reality. In 1961, an astronomer named Frank Drake sat down at the National Radio Astronomy Observatory in Greenbank, West Virginia, and formulated an equation, now known as the Drake equation. It represented the first rigorous attempt to quantify how many actively communicating civilizations might coexist within our galaxy at this very moment. It functions by multiplying a chain of probabilities. The rate of new star formation, the fraction of those stars that host planets, the percentage of those worlds that develop life, that go on to develop intelligence, that create detectable technology, and are actively transmitting at this specific instant. When Drake initially ran the calculations, many of these variables were based on absolute guesswork. We lacked knowledge regarding the commonality of planets. We didn't know how often life-sustaining environments appeared. We were essentially projecting estimates in the dark. We are no longer estimating in the dark. The Kepler Space Telescope, operating from 2009 to 2018, identified and confirmed over 4,000 exoplanets. Its discoveries fundamentally altered our baseline assumptions. Planets are not anomalies, they are ubiquitous. Nearly every star possesses them. The fraction of stars hosting planetary systems proved to be staggering, close to 100%. Furthermore, rocky planets situated within habitable zones are not commonplace, but they are certainly not vanishingly rare either. When you incorporate this modern empirical data into Drake's equation, even using exceptionally conservative figures for the biological and societal variables we still do not know, the result consistently yields thousands, perhaps even millions, of technological civilizations within the Milky Way alone right now, all potentially broadcasting, all potentially detectable. And that is just within our single galaxy. There are an estimated 2 trillion more in the observable universe. Therefore, according to the numbers, the universe should be deafeningly loud. It should be saturated with signals, historical artifacts, technological signatures, and evidence of astro-engineering on scales we could hardly fail to notice. At the very minimum, we should have detected something entirely by accident. A stray transmission, an unnatural pattern in the cosmic background radiation. Something. In 1977, a researcher named Jerry Amon was meticulously analysing data recorded by the Big Ear Radio Telescope at Ohio State University. He was examining a computer printout. Remember, this was 1977. Everything was still processed on physical paper. He was scanning columns of numerals representing varying signal intensities, and there he located it. A narrow band signal exactly at 420 ms, This is the hydrogen line, the precise frequency that theoretical physicists had long speculated an intelligent civilization would utilize for broadcasting. The signal persisted for 72 seconds, which was the maximum window the stationary telescope could observe that specific point in space. It registered so dramatically above the surrounding background cosmic noise that Eamon famously circled it on the paper printout and penned a single word in the margin: "Wow." That date was August 15th, 1977. Since that day, astronomers have been desperately attempting to redetect that signal. It has been 47 years of dedicated follow-up observations using multiple telescopes at various frequencies. That exact patch of the sky has been checked hundreds of times. The signal never returned, so that is where we stand. One solitary anomaly recorded in 65 years of patient listening. A single transmission that appeared once and immediately vanished, juxtaposed against a mathematical calculation stating the heavens should be screaming at us. In the end, Fermi's question was never actually about flying saucers. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. We will move from the measurable quiet sky to the arithmetic of expected civilizations, to the hypotheses that survive modern searches. And when the investigation closes in, you will see why the most terrifying solutions are also the hardest to dismiss. Billions of stars fill the Milky Way, and billions of years have passed since it formed in rotating dusty layers. Planets are common, chemistry is universal, and evolution has had absurd time to iterate through chance and selection. By every naive expectation, the sky should be loud with evidence of others, bright, messy, undeniable. Instead, the sky stays quiet in the ways that matter, as if the galaxy learned to whisper. We can count the milestones that should have made the galaxy crowded, and we can picture them as a montage. Heavy elements are forged in stellar cores and supernova shocks, then scattered like ash into future systems. Rocky worlds assemble from protoplanetary disks, and their surfaces cool until crusts can hold shape. Oceans stabilize when pressure and temperature allow liquid water to persist, and atmospheres cycle for eons through volcanism, weathering, and photochemistry. On Earth, life appeared early in geological terms, then intelligence arrived late but decisively, after countless experiments in form. In a galaxy this old, even one civilization per million stars would still mean thousands, spread across spiral arms like distant cities. If technology scales, even modest expansion should leave detectable traces, because energy use has consequences. Waste heat must go somewhere, and large-scale engineering must change light and motion. Even careful societies would struggle to be perfectly invisible across millennia. Now cut to the measurements that refuse to cooperate, and hold the shot long enough to feel the absence. Radio surveys sweep the sky and return mostly noise, pulsars, and the familiar hiss of cosmic background. Infrared maps show dust, stars, and galaxies, but not the smooth excess glow you would expect from star-spanning industry. Optical telescopes see transits and spectra, but not obvious megastructures casting unnatural shadows. Our instruments keep finding nature, and almost never find intent, even when we look where intent should be easiest. This is the emotional shock at the center of the Fermi paradox, and it lands like a mismatch between two graphs. It is not a debate about whether aliens exist somewhere in the abstract. It is a contradiction between plausible rates and missing observables, between what should accumulate and what does not. Given the age of the galaxy and the ease of physics, where are the detectable traces? Where are the signals, the artifacts, the engineered energy budgets, the unmistakable fingerprints that do not look like stars? The paradox is measurable because it is about what should leak into our telescopes, even without permission. A civilization does not need to talk to us to be noticed, and it does not need to care. It needs only to use energy, move matter, and persist long enough for those actions to leave statistical scars. Communication is one techno-signature, but not the only one, and not necessarily the most durable. The absence is not philosophical, it is statistical and instrumental, and that makes it harder to ignore. We start with the simplest expectation, because simple expectations are where the silence first becomes strange. If intelligent life is not extremely rare, some fraction should build radio transmitters, if only for local convenience. Some fraction should build powerful radars, navigation beacons, or interplanetary links, because coordination across distance rewards precision. Some fractions should spread, mine, and reshape environments, producing heat and unusual chemistry as a byproduct. Even if most are quiet, a few should be loud by accident through leakage, misalignment, or sheer scale. Then we look at the actual search, and we treat it as a real experiment with limits. SETI has listened for about 65 years, using real dishes, real receivers, and real budgets that rise and fall with politics. It has scanned targeted stars and wide fields, and it has combed narrow bands and broader ones to catch both beacons and chatter. It has searched near the hydrogen line because it is a natural meeting place, a frequency marked by the most abundant element. It has built catalogues of non-detections that are not nothing, because each null result constrains what kinds of transmitters could hide nearby. But silence is not uniform and our search is not complete, which is the first honest relief. We have not monitored every star continuously for decades, and we have not watched the same targets at the same time. We have not covered every frequency with the same sensitivity, and we have not always separated weak signals from terrestrial interference. We miss short bursts that happen once and never repeat, and we miss signals that drift in frequency like a transmitter on a moving planet. We miss tight beams that sweep past us like a lighthouse we never face, and we may never know they existed. We also bias the search toward what we know how to build, which is both practical and dangerous. Radio is cheap and transparent through the interstellar medium, so we listen for radio and we build our expectations around it. Yet advanced technology might not broadcast in our bands at all, or it might treat radio as a primitive leakage to be eliminated. It might use lasers, neutrinos, gravitational waves, or something that looks like ordinary astrophysics until you know what to subtract. The paradox survives because even broad searches still imply emptiness in places that should be crowded, especially for the loudest, most wasteful possibilities. The tension is often summarized with the Drake equation, which is famous because it is both simple and unsettling. It multiplies rates of star formation, planet occurrence, habitable worlds, life, intelligence, technology, and longevity into a single expected number. It looks like a calculator for civilizations, but it is really a map of ignorance drawn as multiplication. Each term is uncertain, and some terms are not independent, which means the product can be misleadingly confident. Still, even conservative guesses can yield more civilizations than the sky seems to allow, and that is why the equation keeps returning. Take only what we now know with confidence, and the early terms already push the count upward. Stars are plentiful, and planets are common, including small rocky ones that resemble Earth in size. Many systems are older than the Sun, and many have stable energy sources for billions of years, which is time enough for complexity. If life emerges on even a small fraction, the numbers climb quickly because the galaxy is large. If technological phases last long, the galaxy should contain overlapping civilizations, and overlap should create detectable clutter. But the Drake equation hides a trap, and the trap is how our minds treat uncertainty. We tend to treat the terms as separate coin flips, when they may be linked by deeper bottlenecks in chemistry, geology, or evolutionary dynamics. A single hard step could dominate everything, collapsing the expected count to near zero even with abundant planets. Or multiple steps could correlate, making the product misleading, because success in one term implies constraints on another. The equation generates tension, then forces us to ask which assumption breaks first and whether the break is behind us. One reason the paradox grips us is that it occasionally offers a hint, then withdraws it, like a signal fading at the edge of reception. In 1977, the Big Ear radio telescope detected a strong narrowband signal, and the context matters. Big Ear was designed for sky surveys, and its beams swept the heavens as Earth rotated, letting sources drift through. The signal lasted about 72 seconds, consistent with a source passing through the beam rather than a local transmitter. Its frequency sat near the hydrogen line, where many would choose to transmit, and the printout received a handwritten note. Wow! The wow signal remains a hinge because it is both compelling and incomplete, and the camera loves that contradiction. It was never seen again, despite follow-up attempts and decades of better instruments that could have confirmed a repeating beacon. It could have been interference, a rare natural emission, or a transient human source reflected in an unexpected way. It could have been a deliberate beacon that never repeated, or a beam that swept once and moved on. One event can anchor hope, and also distort judgment, because humans are pattern hunters. The lesson is not that the signal was alien or not, because that question may be unanswerable. The lesson is how hungry a civilization becomes when the data are sparse, and how quickly narrative fills gaps. We will overinterpret a single anomaly because the alternative is a universe that does not answer, and silence feels personal. That hunger is part of the story, because it shapes what we search for and what we fear, and it can lead us to chase ghosts. Then the evidence base changes, and the paradox sharpens rather than fades. The exoplanet revolution turns philosophy into census, and it happens within a human lifetime. Kepler showed that planets are the rule, not the exception, by watching tiny dips in starlight across a fixed patch of sky. Those dips, repeated with clock-like regularity, revealed worlds by the thousands, many in compact systems unlike our own. TESS expands the catalogue around bright nearby stars where follow-up is possible with spectroscopy and precision timing. We now have thousands of confirmed worlds and statistical maps of their sizes and orbits, and the maps look crowded. With that census comes a new kind of measurement, and it is more intimate than a radio sweep. We can observe atmospheres by transit spectroscopy and eclipse mapping, teasing out molecular fingerprints from light filtered through a thin rim of gas. We can search for gases that should not coexist without replenishment, because chemistry tends toward equilibrium unless something keeps pushing. We can test models against data instead of imagining Earth clones in the dark, and we can quantify uncertainty rather than merely argue. The question shifts from how many planets exist to how many are chemically alive, and whether life leaves a detectable imbalance. JWST changes the rules because it pushes sensitivity into regimes we can argue about with numbers, not just hope. It can detect molecular features in some small planet atmospheres, especially around cool stars where transits are deeper. It can distinguish carbon dioxide from methane under certain conditions, and it can measure water vapor when clouds do not erase the signal. It can reveal hazes and clouds that flatten spectra, and it can show how hard interpretation really is when the data are thin. It does not solve the paradox, but it constrains it, and constraints are how mysteries become science. A live case study sits at the edge of our reach, and it illustrates both promise and peril. K2-18b is a sub-Neptune orbiting a cool dwarf star, about 120 light-years away, close enough to be tempting. It lies in a region where temperatures could allow liquid water under some scenarios, depending on albedo and atmospheric structure. Some researchers propose it could be a Hycean world with a hydrogen-rich atmosphere over an ocean, a planet unlike Earth, but potentially habitable in its own way. It is not Earth, but it is observable, and observability is power. Early reports suggested methane and carbon dioxide in its atmosphere, which is plausible and not itself a sign of life. Later claims argued for dimethyl sulfide, a molecule associated with biology on Earth, because most known DMS on our planet comes from marine organisms. Those claims were contested, and the statistical confidence and modelling assumptions became the story, rather than the molecule itself. The debate shows how easily noise, systematics, and priors can masquerade as discovery, especially when the signal is a small bump on a complicated spectrum. Biosignatures are hard because atmospheres are messy and data are thin, and nature loves ambiguity. Clouds flatten spectra and hide deeper layers, turning rich chemistry into a nearly featureless line. Different mixtures can produce similar features, creating degeneracies that cannot be resolved with one instrument or one wavelength range. Stellar contamination can imprint false signals when star spots and faculae change the apparent spectrum during transit, and that effect can mimic molecules. Even a real molecule may have non-biological sources under alien chemistry, because planets can surprise us with pathways Earth never uses. So the paradox is not solved by one promising planet, and it is not dismissed by one contested claim, because science rarely turns on a single data point. Instead, the paradox becomes more urgent because the universe looks more habitable than we assumed, at least in raw opportunity. We now know there are countless places where life could try, and countless timescales for it to persist. If the sky is still quiet, the explanation must be strong, and it must survive contact with measurement. This documentary is an investigation into that strength, and it treats the silence as evidence with texture. We will treat the silence as evidence, not as a blank page, and we will ask what kinds of worlds it implies. We will examine serious solutions and ask what each predicts we should observe, because predictions are where stories become testable. We will test them against what telescopes have actually seen, and against what they have not yet been able to see, because absence has boundaries. We will start with the comforting answers and see where they fail, one by one, under the pressure of the same quiet sky. Rare Earth argues that complex life is extraordinarily unlikely, so the galaxy can be empty without drama. The Great Filter argues that something kills most civilizations before they become visible, and that the danger may be statistical rather than malicious. Dark Forest argues that civilizations hide because being seen is dangerous, and that silence is a strategy. Berserker scenarios imagine automated predators that erase competitors, leaving a managed emptiness. Simulation arguments claim the silence is a feature of the program, an output shaped by constraints we do not see. Each solution has a cost, and each cost is a clue, because it tells us what we must accept. Rare Earth must explain why life on Earth appeared quickly, and why planets are so common if complexity is nearly impossible. Great Filter must choose where the filter sits, and whether it lies behind us or ahead, which changes dread into relief or relief into dread. Dark Forest must explain coordination without contact, and why hiding remains stable across millions of years despite mistakes and newcomers. Berserkers must explain why the galaxy shows no collateral signatures of their activity, no obvious scars of systematic sterilization. Simulation must explain why the rules look so consistent and wasteful, and why the cosmos bothers with so much unobserved detail. We will not treat these as science fiction, but as hypotheses with observable consequences, because consequences are what telescopes can interrogate. If civilizations expand, we should see infrared waste heat at some scale, even if it is only a fraction of starlight re-radiated at lower temperatures. If they communicate, we should see persistent beacons or leakage in some bands, or at least statistical outliers that resist natural explanation. If they hide, we should see signs of deliberate suppression or camouflage, perhaps as engineered normality where variance should exist. If they are destroyed, we should see the absence of long-lived technosignatures even in old regions, where time should have allowed accumulation. The structure is elimination, not revelation, and that is a harder kind of storytelling. We will narrow the space of explanations using what we can measure today, and we will be explicit about what we cannot. We will keep returning to the same question in different forms, because the same silence echoes across methods. What should a galaxy with technology look like from far away, when you cannot resolve cities but you can measure energy? What does our silence actually rule out, and what does it leave untouched? The dread begins when the comforting interpretation stops fitting, and the camera lingers on our own smallness. The answer might not be that we are alone, and that possibility is not the only frightening one. The answer might be that we are early, fragile, and visible, and that visibility is a phase with a cost. The universe might be full of life that never reaches the stage of leaving durable traces because it stalls at microbes or collapses at complexity. Or it might be full of intelligence that learned to disappear, and that lesson may have been learned the hard way. Cosmic silence can mean emptiness, but it can also mean caution, collapse, or predation, and each interpretation changes how we should feel about our future. It can mean that longevity is rare, and that the window of detectability is short, like a brief flare between darkness. It can mean that expansion is not the default, or that it is punished by physics, economics, or conflict. It can mean that the first civilizations to appear set the rules for everyone else, and that later arrivals inherit a quiet sky as policy. We live at a moment when our own signals are escaping the Earth, and we are only beginning to notice what we radiate. Our radars have been bright enough to be seen across interstellar distances in principle, especially when aimed at asteroids or planets with high power. Our industrial activity changes the spectrum of our planet, and our satellites add artificial glints that a distant observer could, in theory, time and model. We are becoming detectable before we understand what detection implies, and before we agree on what we would want to be. So Chapter 1 ends with a simple claim that will guide everything that follows, and it is meant to feel like a door closing. The paradox is not an abstract puzzle, it is a constraint on futures, including ours. If the sky is quiet for a reason, that reason may apply to us, whether it is rarity, fragility, or strategy. We will now descend from the quiet sky into the possible mechanisms that enforce it, and we will ask which mechanism fits the data without comforting us. The silence feels personal, but the paradox is built from arithmetic and time, not malice. Chapter 1 framed the sky as a wiped crime scene, a place where evidence should linger in plain sight. Chapter 2 asks what the scene should look like if physics is impartial, and if the universe keeps no favourites. Start with the clock that makes the quiet so strange, because the timeline is the first pressure. The Milky Way is more than 10 billion years old, and its oldest stars formed when the galaxy was still assembling from smaller fragments. Many stars in the disk are older than the Sun by billions of years, meaning their planets have had long eras to experiment with chemistry, ecology and technology. Earth has hosted radio for about a century, and space industry for only decades, a blink inside geological time. If technology is a phase that can last, and if it emerges more than once, we should not be first. The tension is not just age, it is overlap, an accounting problem that grows with every extra year. If civilizations arise at any steady rate, even a small one, older ones accumulate like layers of sediment in a river delta. A galaxy that has been making stars for billions of years should contain deep time neighbours, not just peers. We should expect some to be millions of years ahead, not merely centuries because the head start is so large. Even a tiny probability per planet becomes consequential when the trial count is measured in billions. Picture the Milky Way from above, a pale spiral with dust lanes like smoke across a streetlight. The central bulge glows like a crowded city seen through fog, while the arms curl outward in dim, starry ribbons. Each bright knot is a region where stars were born, and each older region is a library of finished experiments. The paradox asks why that library looks unopened, why the shelves show no obvious engineering, no rearranged lighting, no heat where there should be work. Now build the baseline from what we can measure, because the argument begins with astronomy, not imagination. Star formation peaked earlier in cosmic history and then slowed, but it never stopped, and the galaxy kept producing new suns. The heavy elements needed for rocky planets, carbon, oxygen, silicon, iron, accumulated as generations of stars lived and died, scattering enriched material through supernovae and stellar winds. That enrichment matters, because early galaxies were metal poor, and later ones became better at building solid worlds with differentiated interiors. The Milky Way has had multiple waves of planet building as metals increased, and the raw number of planetary systems is enormous, even after pessimistic cuts. Exoplanets turn the first-rate terms from guesses into statistics, and that shift is historically recent. For most of the 20th century, planets were philosophical, inferred from our own system and from theory, with only indirect hints in starlight. Then, in the 1990s, the first exoplanets around Sun-like stars were confirmed, and the flood began. Early detections favoured hot Jupiters, because big planets tug hard and transit deeply, yet even that bias was informative. Kepler, staring at one patch of sky, showed that small planets are common around Sun-like stars, not rare jewels. It also showed that compact multi-planet systems are normal, not exotic, with several worlds packed inside the orbit of Mercury. TESS adds nearby targets where follow-up can test atmospheres and densities, turning dots into physical places with measured mass, radius, and temperature. The key number is not a single rate, but a pattern across many kinds of stars and orbits. Roughly Earth-size to super-Earth-size planets occur frequently within a few tenths of an AU, and the distribution is broad. Many stars host several small worlds, which multiplies opportunities per system in a way the early Drake discussions could not quantify. Even if only a fraction are temperate, and even if temperate is only a first filter, the inventory remains large. The statistics do not promise life, but they do promise venues. When we say common, we should be precise, because the word hides a statistical claim. Kepler's transit method favours close-in planets, yet the corrections still imply that planets are the rule, not the exception. Radial velocity surveys, sensitive to different regimes, reinforce the same broad conclusion, even if the details differ. The galaxy is not a sparse archipelago of solar systems, but a dense ocean of them, most with their own architectures, migration histories, and violent early eras. Then the galaxy's demographics push the count higher, because the Sun is not the typical star. Most stars are M-dwarfs, smaller and cooler than the Sun, dim red embers compared to our yellow-white lamp. They burn fuel slowly, and can shine for trillions of years, far longer than the current age of the universe. That longevity matters, because it stretches the available window for biology, and for any later technological phase. If habitability is possible around them, the universe has vast long-lived real estate, and time becomes even less forgiving. M-dwarfs also compress the habitable zone inward, and that changes everything we can observe. Planets in that zone orbit close, transit often, and are easier to detect, which is why our catalogues are full of them. That observational bias can inflate our confidence about their abundance if we forget the selection effects. Yet even corrected, M-dwarf planets appear common, and many are roughly Earth-sized, which keeps the paradox alive. The most numerous stars also offer the most numerous test cases, and that combination is hard to ignore. But habitable zone is not habitability, and the distinction matters because the phrase sounds more certain than it is. The zone is a temperature estimate for liquid water on a surface, assuming an atmosphere that behaves in a simplified way. Habitability is a coupled system of atmosphere, ocean, geology, and star, with feedback loops that can stabilize or destroy. A planet can sit in the zone and still be sterile or hostile, or locked in a climate state that never allows chemistry to get started. The map is not the territory even when the map is drawn with equations. The habitable zone is often drawn as a neat ring around a star, a green band on a diagram. In reality, it is a moving target, because stars brighten over time and planets evolve internally. Even on Earth, habitability has not been constant, and life had to survive ice ages, impacts, and atmospheric shifts. Early Earth likely endured a faint young sun and a different air chemistry, yet it remained wet. The zone is a starting line, not a finish. Close-in planets around M-dwarfs face tidal locking, a consequence of gravity and time. Over millions of years, tidal forces can synchronize rotation and orbit, so one hemisphere always faces the star. One side can bake under constant daylight, while the other freezes in permanent night, unless the atmosphere transports heat efficiently. Some models allow stable climates with thick air and active circulation, and oceans can help redistribute energy through currents. Yet these outcomes depend on composition, pressure, and cloud behavior, which can flip from protective to catastrophic. The zone becomes a question, not an answer, because the climate is an engineered compromise by physics. There is also the matter of tidal heating, which can be a gift or a curse. If a planet's orbit is slightly eccentric, gravitational flexing can warm its interior, driving volcanism and recycling gases. Too much heating, however, can trigger runaway volcanism or keep the surface molten, erasing the gentle conditions we imagine. The same mechanism that keeps Europa's ocean liquid could, on another world, sterilize the surface. Again, the zone is not a promise, it is a boundary condition. M-dwarfs are also magnetically active, especially when young, and youth can last a long time for small stars. They flare in ultraviolet and X-rays, and they can erode atmospheres over time through photochemistry and particle bombardment. A planet may need a strong magnetic field, a thick atmosphere, or rapid replenishment through volcanism and impacts. Otherwise, the zone becomes a stripping ground, where water is split and hydrogen escapes into space. The star's calm middle age may arrive only after the planet has already been sandblasted. The visual is stark. A red star flickers, then erupts in a white-blue flash, and the planet's upper atmosphere glows like a thin veil. Charged particles stream outward, and the night side briefly shimmers with auroral light. Over long spans, that veil can be peeled away molecule by molecule, leaving behind heavier gases and a drier world. If life needs stability, the early violence of small stars could be a common obstacle. The paradox survives, but it gains texture, more ways to fail. Water inventories complicate the picture in both directions because water is not a single knob. Some planets may be too dry, with little surface water to buffer climate and drive weathering cycles. Others may be water worlds with deep oceans that suppress nutrient cycling and isolate the seafloor from the atmosphere. Too much water can bury continents and stall key geochemical feedbacks, leaving a planet chemically quiet. Too little water can leave it brittle and desert-like, with limited pathways for complex chemistry. The same molecule that makes life possible can also reshape the entire planetary machine. Even the presence of water can be deceptive, because it can hide in mantles and minerals. Earth's oceans are only a fraction of its total water budget, and other worlds may store most of theirs underground. A planet can look dry from space and still have internal reservoirs, or look wet and still lack the right chemistry at the surface. What matters is not just quantity, but accessibility, cycling, and chemical context. Plate tectonics is another hidden variable that Drake-style counts often ignore because it is difficult to detect remotely. On Earth, it stabilizes climate through carbon cycling and drives long-term nutrient recycling, moving phosphorus and other essentials from rock to ocean. It also creates diverse environments, coastlines, shallow seas, mountain weathering that may have helped complexity. We do not know how common it is or whether it is required, and the physics is still debated. We only know it is not guaranteed, because a similar sized planet like Venus appears to have taken a different path. The difference between a blue planet and a furnace may hinge on interior mechanics we cannot yet measure. Tectonics also ties into interior heat, which depends on formation history and radioactive elements. Too little heat and the planet becomes geologically dead, with a stagnant lid and weak recycling. Too much heat and the surface can be dominated by volcanism, with an atmosphere constantly rewritten. Habitability is therefore a spectrum of dynamic balances, not a checkbox. The paradox is not naive optimism, but the recognition that even narrow windows, multiplied by vast numbers, still matter. So pessimism is justified, but it does not automatically dissolve the paradox because the numbers are still large. Even if only a small fraction of temperate planets are truly habitable, the galaxy still holds billions of candidates. Even if life is rare, time is long and the experiment has been running for eons. Even if intelligence is rarer, the math still bites, because we do not need many successes to change the sky. A single long-lived success can outweigh 1,000,000 failures. To see why, reframe the Drake equation into stages that do not blur together, because the blur hides where the real uncertainty lives. First is the existence of life, which may be microbial and quiet for billions of years, leaving only subtle chemical traces. Second is the rise of technological intelligence, which may be contingent, fragile, and shaped by accidents of evolution. Third is detectability, which is often treated as automatic but is not, and it is where the paradox sharpens. The question is not merely are they out there, but would we notice if they were? On Earth, life appeared early, but complex multicellular life took a very long time to arrive. Oxygenation, eukaryotic cells, and stable ecosystems were not quick steps, and each depended on planetary conditions staying within bounds. Intelligence capable of technology is even more recent, and it may not be a convergent outcome everywhere. That history is a warning. The path can be slow and it can be narrow, even on a world that works. If evolution is a maze, not a ladder, then many worlds may never find the same exit. Detectability is the hidden variable that casual Drake discussions ignore because it feels like an afterthought. A civilization can exist and still be invisible to our methods, either by accident or by design. It can communicate in ways we do not monitor, using frequencies, encoding, or mediums that leave no obvious trace. It can also be detectable without trying, simply by using energy at scale and changing its environment. The paradox is less about messages and more about side effects. This is where the paradox becomes sharpest, because it stops being about hope and becomes about footprints. The strongest contradiction is not about life, it is about long-lived high-impact civilizations. If any fraction of civilizations become powerful and persist, their footprints should accumulate, and accumulation is hard to hide. The sky should contain at least a few obvious outliers, stars or regions that look wrong. Why does the cosmic ledger show so few suspicious entries? That brings us to the trap inside the L term, the longevity factor, which quietly dominates the arithmetic. People treat L as a final multiplier, like a footnote at the bottom of the page. In reality, L controls overlap, and overlap controls whether we should expect neighbours right now. Even rare civilizations can overlap if the rare ones last long, and the galaxy has had time to let the long-lived dominate. A short-lived civilization is a spark, but a long-lived one is a lighthouse. Think of it as a bathtub with a slow faucet and a drain, because the metaphor is simple and the math is merciless. The faucet is the birth rate of technological civilizations, perhaps 1 per million years, perhaps less. The water level is the number alive right now, the ones whose light could reach us today. If the drain is slow, the tub fills even with a weak faucet, and the level becomes hard to keep near zero. The paradox is the empty tub in a house with ancient plumbing. So to keep the galaxy quiet, something must reliably shorten L, or reliably reduce detectability, and it must do so across many independent histories. It is not enough that civilizations are uncommon, because uncommon plus long-lived still produces overlap. It is not enough that intelligence is hard, because hard plus deep time still allows occasional breakthroughs. The silence implies either extreme rarity, extreme brevity, or extreme stealth, and each option has consequences. Each option also makes a prediction about what we should find as our surveys improve. Now define what we mean by detectable in physical terms, because detectable can sound like a social choice. Technology is not magic, it is work, and work requires energy, whether it comes from sunlight, fusion, fission, or chemistry. Energy use produces waste heat because thermodynamics is not negotiable, and entropy must be exported. The more energy a civilization controls, the more it becomes an astronomical object, not just a cultural one. At high enough scale, industry becomes a climate and then a spectrum. This is the logic behind the Kardashev scale, proposed in the 1960s as a way to anchor speculation to physics. Type 1 is planetary scale energy use, comparable to the sunlight hitting a world's cross-section. Type 2 is stellar scale, capturing a significant fraction of a star's output, which implies structures or swarms that intercept light. Type 3 is galactic scale, reshaping energy budgets across many stars, a civilization that becomes part of the galaxy's luminous ecology. The scale is not a prophecy, but it is a ruler, one that measures footprints instead of intentions. The scale is crude, but the physics is not, and that distinction matters. Any large-scale industry must dump entropy into space, and the easiest way is radiation. If it captures starlight, that energy must be re-radiated at lower temperatures, because the collectors and habitats cannot glow like stellar photospheres. The signature shifts from visible light toward infrared, because the radiator is cooler than a star, and cooler objects peak at longer wavelengths. The universe is transparent to heat in many bands, and heat carries the story outward. This is not a guess, it is the Stefan, Boltzmann law in narrative form. A star radiates like a hot furnace, peaking in visible light, while a warm structure radiates like a heated rock, peaking in infrared. If you wrap a star in collectors, you do not erase its energy, you change its color in the sky. The paradox asks why we do not see many stars that have been recolored by industry. If engineering is common, why does starlight look so natural? Dyson's idea was not a single rigid shell, and the popular image is misleading. It was a family of possibilities, motivated by the recognition that a civilization might expand its living area and energy capture gradually. Swarms of collectors, rings, habitats, and mirrors can all intercept starlight, and they can be built in stages. The engineering details vary, but the thermodynamic consequence is similar, almost unavoidable. Starlight in, infrared out. Imagine a star that should look like a sharp point of white-yellow light, but instead it is dimmer in visible wavelengths. Now imagine that missing light reappears as a smooth glow in the mid-infrared, like a warm ember surrounding the star. In a telescope image, it would not look like a neat sphere, but the spectrum would betray it. That is the kind of signature astronomers can search for, because it is not subtle if the coverage is high. It would be a mismatch between temperature, brightness, and expectation. That makes infrared surveys a kind of forensic tool, and the history of those surveys matters. IRIS mapped the sky decades ago and found dust, stars, and galaxies, opening a new window on cold material and hidden star formation. WISE mapped it again with better sensitivity and resolution, cataloguing hundreds of millions of sources across multiple infrared bands. These surveys can constrain how many stars are wrapped in high-coverage collectors, because the sky is not an empty canvas. It is a measured dataset, and anomalies can be counted, revisited, and compared across catalogues. The constraints are not perfect, but they are not nothing, and the absence itself becomes a number. We do not see large populations of sun-like stars with the smooth infrared excess expected from heavy energy harvesting. We do not see many galaxies with the kind of mid-infrared glow that would suggest widespread stellar-scale industry across billions of suns. Absence becomes evidence when the search volume is large, because large volumes should contain at least a few rare things. The sky is crowded with natural infrared sources, yet the specific industrial pattern remains elusive. Astronomers do find infrared excesses, but most are explained by dust, disks, or star formation. Dust grains absorb starlight and irradiate in infrared, producing signatures that can mimic some megastructure scenarios. That is why the search becomes careful, comparing spectra, variability, and spatial distribution, and checking whether the source looks extended like a dusty nebula. The point is not that we have ruled everything out, but that we have not found the obvious cases. The universe offers many disguises, and nature is an expert at making infrared light. There are loopholes, and they matter for later chapters because the universe allows cleverness. A civilization could radiate waste heat at very low temperatures, pushing emission into far infrared or microwave bands where backgrounds are higher. It could use energy efficiently, lowering total throughput, or shift activity underground and reduce radiating area. It could also build in ways that mimic dust, hiding inside astrophysical noise, and the line between natural and engineered can blur. Yet every loophole is a trade. Less visibility often means less power, less expansion, or more complexity. But each loophole has a cost in scale or strategy, and costs accumulate as requirements. Low-temperature radiators require enormous surface area, because cooler objects must be larger to dump the same power. Perfect camouflage requires discipline across millennia and across many independent actors, not just one decision. The more powerful the civilization, the harder it is to be perfectly quiet, because every additional watt must go somewhere. At some point, hiding becomes its own mega-project. Radio silence fits the same pattern, and it is the most familiar part of the story. We have not searched everything, and we have not listened continuously, and our instruments have limits. Yet we have surveyed enough nearby stars to constrain very loud beacons aimed broadly at the sky. We have also looked for narrowband signals that nature rarely produces, the kind that stand out against cosmic noise. The lack of repeatable artificial signals is a data point, even if it is not a verdict. It tells us that the obvious careless transmitters are not common in our neighborhood. The deeper argument is that communication is optional, but energy is not. And that is where the mystery tightens. A civilization can choose not to talk, or it can speak in ways we do not recognize. It cannot choose not to obey thermodynamics, and it cannot choose to leave no byproducts if it does large-scale work. It can choose not to expand, but it cannot choose to have no physical consequences. Detectability is therefore about footprints, not invitations, and footprints are harder to erase. Now add the colonization timescale, which turns the paradox from abstract to urgent, because it introduces motion. The Milky Way is about 100,000 light-years across, a disk with a thin thickness compared to its width. A self-replicating expansion front does not need light speed, and it does not need a single empire. It needs persistence, redundancy, and time, the same ingredients that make biological invasions effective. The galaxy's geometry, wide, connected, and old, favors diffusion. Even at a few percent of light speed, a wave of probes can cross the galaxy in a few million years, and the math is straightforward. Even slower, with long pauses to build infrastructure, the timescale stays far below the galaxy's age. Compared to 10 billion years, a million years is a blink, and 10 million is still a blink. The galaxy has had time for many such waves, even if they are rare. If expansion ever happens, it has time to happen again and again. This is not a claim that expansion is inevitable, only that it is easy to imagine within known physics. Biology already builds self-replicators, and industry already builds automation, and the gap between them is shrinking. If any civilization chooses expansion and survives, it can seed many systems, not necessarily with people, but with machines and infrastructure. That should create visible artifacts or at least statistical anomalies, because large-scale activity changes environments. Even modest engineering, repeated across thousands of systems, becomes a pattern. The colonization argument also does not require conquest, and the word can mislead. It can be exploration, resource gathering, scientific curiosity, or distributed survival against local disasters. It can be slow and cautious, with low-density settlement and long intervals of quiet. Yet even low-density settlement across thousands of systems should leave some detectable engineering, because the infrastructure must exist somewhere. The galaxy should not look untouched if this has happened even once. A single ancient wave would have had time to leave echoes in many directions. Consider what untouched means in astronomical terms, because we are not expecting billboards. It means stellar populations that match natural distributions, infrared backgrounds dominated by dust and stars, and radio skies filled mostly with pulsars and plasma. It means no regions that look thermodynamically overworked, no neighborhoods with suspiciously altered spectra. It means no large-scale dimming that cannot be explained by interstellar dust. The paradox is that nature seems to be the only artist visible on the canvas. At this point, the paradox becomes a three-way tension between opportunity, time, and silence, and each corner is supported by data. Opportunity comes from abundant planets and long-lived stars, especially the countless M-dwarfs. Time comes from billions of years of head start for older civilizations, a head start that dwarfs our entire history. Silence comes from the lack of clear technosignatures in radio, optical and infrared, despite surveys that have covered huge fractions of the sky. The triangle holds, and it squeezes. So we tighten the question to match what telescopes actually test, because the argument is strongest when it stays measurable. How many civilizations should exist right now that are both old and loud, not just alive somewhere? How many should be using energy at scales that leak into infrared surveys, even if they never transmit a message? How many should have expanded enough to create detectable patterns in stellar populations, even if they avoid attention? If the answer is some, then silence demands a reason. We do not need millions to create a contradiction, and that is the uncomfortable part. We need only a few long-lived outliers, the rare winners that survive the hazards and keep growing. If even one civilization reached Type 2 scale and persisted, its host star could look wrong in a way we can measure. If even one civilization spread widely, some region could show engineered infrared excess or a statistical dip in visible starlight. The absence of even a few is the sting, because the galaxy is so large. This is where pessimistic adjustments are allowed, but they must be honest, and they must respect the scale. Maybe most habitable zone planets are not habitable, and maybe many are sterilized early by impacts or stellar tantrums. Maybe life is rare, or intelligence is rare, or technology is rare, and each step could be a bottleneck. Yet the galaxy is so large that moderate pessimism still predicts some survivors, and survivors are what matter for footprints. The silence pushes us toward extreme pessimism or toward a new variable. That new variable is detectability as a phase, not a constant, and it reframes what quiet might mean. A civilization might be detectable only briefly, during a noisy industrial adolescence when energy use spikes and radio leakage is careless. It might then stabilize, reduce waste, and stop broadcasting, either by efficiency or by cultural choice. Or it might collapse, ending the phase before it spreads, leaving only ruins that fade into geology. Either way, the window can be short, and short windows reduce overlap. We can also separate detectability into passive and active forms, because they carry different assumptions. Active detection is deliberate signaling, which can be absent for cultural reasons, fear or indifference. Passive detection is leakage and waste heat, which scales with energy and infrastructure, and it is harder to suppress completely. The paradox is strongest for passive signatures, because they are rooted in physics, not etiquette. If passive signatures are missing, then either the phase is brief or the scale is rare. Now connect this back to the central question of the documentary, because this chapter is not just counting planets. What does the silence imply about the fate of intelligent civilizations and about our own trajectory? If the universe plays fair, the numbers suggest many tries, scattered across time and space. If the tries rarely become visible, something filters them, and filters are often brutal. If the visible phase is brief, the filter may be a common failure mode that repeats. The quiet is not neutral, it is informative. We are not yet choosing a solution, only narrowing the space, and the narrowing is the point. The quantitative backbone says the galaxy has had time for many experiments, even if the success rate is low. Exoplanet statistics say the raw materials are common, and that small rocky worlds are not special. Thermodynamics says large-scale technology should leave heat, and heat is detectable at astronomical distances. Colonization timescales say persistence should spread footprints widely, even if expansion is cautious. So the quiet sky is not just a lack of messages, it is a lack of accumulated consequences. It is a lack of old neighbours whose waste heat, engineering or expansion should have altered what we measure. It is a lack of stars that look partially dimmed in visible light and strangely bright in infrared. It is a lack of regions that feel worked, as if someone has been rearranging energy flows for a long time. That absence is the pressure that forces the next chapter, because it demands either a missing ingredient or a missing assumption. The universe is not merely silent, it is clean. If the numbers suggest they should be here, then two broad options remain. Either the numbers are wrong, because we are rare in a deep way, rare beyond ordinary pessimism, rare at the level of biology or chemistry or improbable history. Or civilizations are common, but something prevents visibility or survival, and that something may be the real story. In one case, the universe is mostly empty of minds, and our solitude is fundamental. In the other, the universe may be full of attempts, and the silence is a record of what happens to them. Which possibility is more unsettling, being alone or being typical? Then the evidence base changes again because we stop counting planets and start counting failure modes, and that shift is unsettling. We move from fair universe arithmetic to unfair universe mechanisms, the kind that can erase footprints before they accumulate. The next chapter asks where the filter could hide and why it would be so reliable across so many worlds. It asks what could shorten L again and again, or what could make detectability a brief flare. It asks in plain terms what keeps the bathtub empty. This documentary is an investigation into that reliability, and it treats silence as a measurable constraint, not a poetic void. The mirror is not pointed at the stars alone, it is pointed back at us, because we are the only example we can dissect. If detectability is brief, we're already inside the brief part, and the clock is already running. The question is whether we are early in a long story or late in a short one. Rare Earth is the first answer people reach for when the sky stays quiet, because it feels like a statistical sigh rather than a threat. It says microbial life might be common, yet complex life is a lottery win that almost never pays out. It says intelligence is not a trend line climbing with time, but a freak outcome that happens once and then stops. It offers comfort through solitude, then quietly demands we accept extreme improbability as the price of that comfort. The hypothesis splits life into tiers that telescopes cannot easily separate, and that separation matters because our instruments see planets as smudged spectra. Chemistry can make cells, and cells can persist, without ever building forests or reefs visible from space. A planet can host microbes for billions of years and still look dead, because microbial metabolisms can hide under oceans, ice, or thin atmospheres. Rare Earth claims the real bottleneck is not life itself, but complexity that changes worlds in ways a distant observer can notice. Chapter 2 argued that time and numbers should produce at least a few loud survivors. Rare Earth answers by shrinking the success rate until even the galaxy's scale cannot help, like turning a cosmic lottery into a game with almost no tickets. The question becomes whether Earth's history looks like a typical path that many worlds follow, or a chain of near misses that only happen to hold. Start with the first major bottleneck that Earth may have barely cleared: eukaryogenesis, the birth of complex cells. Eukaryotic cells have nuclei that protect DNA, internal scaffolding that shapes the cell, and energy-rich organelles that function like microscopic power plants. On Earth, it likely involved endosymbiosis, a merger between once independent microbes, where one cell took up another and did not digest it. The mitochondrion, with its own remnant genome and bacterial ancestry, is the fossil of that ancient bargain. Rare Earth treats that merger as a rare accident, not an inevitable upgrade, because it required compatibility across many dimensions at once. The host had to tolerate an invader. The invader had to provide energy rather than poison, and gene transfer had to stabilize the partnership over evolutionary time. The cell also needed new systems for transport, regulation, and division, because bigger cells face diffusion limits that small bacteria avoid. In plain terms, it is not just a new part, it is a new operating system. The argument is simple and unsettling. Prokaryotes dominated Earth for most of its history, and they were already exquisitely adapted to almost every niche the planet could offer. If complex cells were easy, why did they take so long to appear, even with oceans full of life experimenting endlessly? If they were hard, then most biospheres may never pass the microbial ceiling, no matter how long they remain wet. But the counter-argument is also strong, and it weakens the comfort. We have only one data point, and timing alone cannot prove improbability, because a late event can still be likely under the right preconditions. A step can be slow because conditions were not ready, not because the step is nearly impossible in principle. Evolution can also wait for ecological openings, not just for mutations, and Earth's early environment was chemically turbulent in ways we barely reconstruct. In visuals, this is where the camera can linger on a dark Archean ocean, iron-rich, greenish under a dimmer sun, while microbial mats ripple like living skin. The world is alive, but it is quiet in the way bacteria are quiet, with no trees to cast shadows and no animals to stir the water. Rare Earth asks us to imagine that most living planets look like this forever. biologically busy yet geologically and visually subtle. Next comes multicellularity, another step rare Earth treats as fragile, even though it sounds like a natural scaling up. Multicellular life requires cooperation, differentiation, and control of cheaters, because any cell that grabs resources without contributing can undermine the whole body. It also requires enough energy and nutrients to support larger bodies, plus developmental programs that build organs in the right places. Earth shows multiple origins of multicellularity in animals, plants, fungi, and several algae, which hints that the basic move may be easier than eukaryogenesis. Rare Earth responds by narrowing the claim, and the narrowing is the tactic that keeps it plausible. It says simple multicellularity may be common, yet complex multicellularity with organs is rare, because it demands stable long-term selection for cooperation. It says large bodies demand stable climates, oxygen, and long uninterrupted time, because large organisms tend to have slower reproduction and smaller populations. It says most worlds get stuck at mats, films, and microbial reefs, where evolution can be rich but never becomes loud. To picture that, imagine a shoreline at low tide where the ground is a slick layered carpet and every colour is a different microbial guild. There are no footprints, no shells, no bones, only chemistry and sunlight and the slow churn of tides. Is that a failure, or simply a different kind of success that never needs animals? Rare Earth quietly assumes that what we call success is the rare branch, not the trunk. Then comes sex, which looks like a paradox even on Earth. Sexual reproduction is costly, risky, and complicated compared to cloning, because it requires finding mates and producing specialized cells. It also breaks up successful gene combinations, which seems wasteful when a body already works. It persists because it accelerates adaptation and purges harmful mutations, especially in changing environments where parasites and competitors keep moving the target. Rare Earth frames sex as a contingent invention that might not appear elsewhere, and it points to the fact that many lineages thrive without it. Yet biology again pushes back against the pessimism, because genetic exchange exists in many microbial forms, even without sex as we know it. Bacteria swap plasmids, viruses shuttle genes, and cells can absorb DNA from their surroundings, which means evolution has multiple ways to shuffle the deck. The deeper question is whether large complex organisms can persist without robust recombination, or whether long-term complexity tends to demand it. Then come nervous systems and complex behavior, which are not automatic products of multicellularity. Neurons require specialized signaling, fast coordination, and developmental control, and they only pay off when rapid response matters. Complex brains require sustained energy and long childhoods, because learning takes time and neural tissue is metabolically expensive. Rare Earth argues that intelligence is not the default endpoint of complexity, but a costly niche strategy that only sometimes wins. Earth's timeline supports that caution in a way that feels personal, because it reminds us how long the planet went without anything like us. Animals existed for hundreds of millions of years without building radios, and many were successful in ways that did not require abstract thought. Dinosaurs ruled for longer than mammals have existed, yet left no technology, no cities, no deliberate signals in the sky. Intelligence that makes tools may be a narrow peak, not a broad plateau, and evolution does not climb peaks unless the terrain pushes it. Still, convergent evolution complicates the story, because it suggests that certain problems have limited good solutions. Eyes evolved multiple times because sensing light is useful in many niches, from shallow seas to forest floors. Wings evolved multiple times because flight is a powerful advantage, even if the engineering differs between insects, birds, and bats. If certain solutions keep reappearing, then maybe cognition also reappears under common pressures, especially where social competition rewards prediction and deception. Rare Earth answers with contingency, not denial, and that distinction is important for tone. It says convergence works for local problems, not for open-ended intelligence that can generalize across domains. It says brains are expensive, and many stable ecosystems reward efficiency over curiosity, because calories saved can matter more than ideas. It says technology requires not just intelligence, but hands, fire, and social structure, plus a pathway to cumulative culture that does not collapse. That brings us to the oxygen problem, the most famous rare earth lever, and the one that sounds most like a clean chemical gate. Complex animals on Earth rely on high oxygen to support large bodies and high metabolism, because oxygen enables efficient energy extraction in cells. Yet Earth did not start oxygen-rich, and it did not stay stable by default, because oxygen is reactive and loves to bind with rocks. Oxygen rose in steps, and each step could have failed, stalled, or reversed if sinks remained hungry. The Great Oxidation Event changed the planet around 2.4 billion years ago, and it was not a gentle sunrise. Photosynthetic microbes produced oxygen, but sinks in rocks and oceans consumed it, especially dissolved iron that rusted out of seawater. When sinks saturated, oxygen accumulated and rewrote chemistry, transforming minerals, altering ocean nutrients, and likely triggering climatic shocks. Rare Earth treats this as a knife-edge transition, not a smooth inevitability, because the balance between sources and sinks could have stayed tipped the other way. Then oxygen rose again much later, during the Neoproterozoic oxygenation, and that second rise may have enabled large animals and complex ecosystems. The timing is suspiciously late, and it suggests long delays are possible even on a living world with plenty of sunlight. It also hints that oxygenation might require tectonic recycling, nutrient delivery, and burial of organic carbon in just the right proportions. Rare Earth argues many planets never reach sustained high oxygen, even if they host thriving microbial seas. For visuals, oxygen can be shown as a pale blue haze creeping into an atmosphere, while the surface shifts from dark basalt to rusted reds. The ocean can fade from green to deep blue as iron precipitates out, leaving clearer water that changes light penetration. It is a planetary makeover driven by microbes too small to see, which is precisely why Rare Earth finds it so precarious. Oxygen is also unstable in a way that complicates remote detection, and this is where the comforting simplicity breaks down. It can be produced abiotically by photolysis of water, with hydrogen escape, especially on planets that lose water to space. It can also be hidden by rapid consumption in oceans and crust, where reduced minerals act like a chemical sponge. A telescope can see oxygen and still be fooled, or miss oxygen and still miss life, because atmospheres are dynamic systems, not static labels. False positives matter because they can inflate optimism, and they can make a dead world look alive. A dry planet around an active star can build oxygen without biology, because ultraviolet light splits molecules and the lightest atoms drift away. A runaway greenhouse can strip water and leave oxygen behind, creating an oxidizing atmosphere over a sterilized surface. Without context, oxygen can be a misleading headline, not a verdict, and headlines are not science. False negatives matter because they can hide real biospheres, and they can make a living world look sterile. Early Earth had life for a long time with little atmospheric oxygen, because production was balanced by sinks, and because oceans buffered the gas. A planet can host abundant microbes and still show weak oxygen features, especially if biology uses different metabolisms or if oxygen stays dissolved. Even a productive biosphere can be masked by haze, clouds, or different chemistry that smears spectral lines into ambiguity. So Rare Earth leans on oxygen, but oxygen also undermines certainty, which is the chapter's recurring rhythm. The same gas that may enable animals is hard to interpret at distance, because it sits at the intersection of geology, biology, and stellar radiation. The more we learn about atmospheric pathways, the more ambiguous the signature becomes, and ambiguity is the enemy of easy comfort. The paradox does not yield to one molecule, no matter how iconic that molecule feels. Now shift from biology to planetary engines, because Rare Earth is also geology, and geology is slow power. Earth stays temperate partly because of the carbon-silicate cycle, a long feedback between weathering and volcanism that acts like a planetary thermostat. When the planet warms, weathering speeds up and draws down CO2, because rain and chemical reactions accelerate. When it cools, weathering slows and volcanism rebuilds greenhouse gases, restoring warmth over millions of years. Plate tectonics may be the key driver of that cycle on Earth, because it keeps the surface young and the interior connected to the air. Subduction recycles carbonates into the mantle and returns CO2 through volcanism, completing the loop rather than letting carbon lock away forever. Tectonics also builds continents, shallow seas, and nutrient fluxes that feed productivity, creating varied habitats that can drive evolutionary experimentation. Rare Earth argues that without tectonics, climates drift into extremes, either freezing under low CO2 or overheating under unchecked greenhouse buildup. The problem is that tectonics is hard to predict on exoplanets, and it is even harder to confirm from light years away. It depends on interior heat, water content, lithosphere strength, and mantle convection, which are properties we infer indirectly at best. A planet can be Earth-sized and still be stagnant lid, like a scaled-up Mars, where the crust does not recycle and volcanism may be sporadic. If stagnant lid worlds dominate, stable climates may be rarer than habitable, zone diagrams suggest, because the zone only tells you about sunlight. But the necessity is debated, and the debate matters for comfort because it leaves room for alternative Earths. Some models allow carbon cycling without plate tectonics through volcanism and weathering on a stagnant lid, especially if cracks and hotspots keep exposing fresh rock. Episodic resurfacing can also recycle volatiles in bursts, resetting atmospheres on long time scales even without continuous subduction. Earth may be one stable mode, not the only workable mode, and rare Earth must argue that other modes usually fail. Magnetic shielding is another rare Earth pillar, often simplified into a single checkbox, even though real magnetospheres are messy. A strong magnetosphere can deflect stellar wind and reduce atmospheric erosion, and it can also shape radiation belts that change surface exposure. It can protect the surface from charged particles, depending on atmosphere thickness and chemistry, because air itself is a shield when it is deep enough. Rare Earth argues that without a dynamo, many planets lose air and water, and with them the long-term stability complex life might need. Yet magnetism is not a clean gate, and the solar system itself is the counterexample sitting in plain sight. Venus has no strong global field and still has a thick atmosphere, although its water history and surface conditions are hostile. Mars had a field early, and still lost much of its air, partly due to low gravity and other factors that make escape easier. A thick atmosphere can also shield a surface even without a strong magnetosphere, which means the checkbox can mislead. The argument becomes sharper around M dwarfs, where stellar winds and flares are intense, and where most stars in the galaxy actually live. Close inhabitable zone planets face stronger particle flux and higher XUV radiation, because they must orbit near the star to stay warm. Atmospheric stripping can be severe during the star's long active youth, when flares and coronal mass ejections are frequent. Rare Earth uses this to claim most habitable zone planets are actually hostile, at least during the very epochs when life would be trying to gain a foothold. But habitability around M dwarfs is not settled, and the uncertainty cuts both ways, which keeps the mystery alive. A planet can retain an atmosphere if it starts with enough volatiles, or if volcanism replenishes losses faster than space can take them. Magnetic fields might be stronger on tidally locked planets due to different interior dynamics, although that remains contested in models. Oceans can transport heat and prevent atmospheric collapse on the night side, turning a locked world into a planet with a permanent twilight band rather than a frozen tomb. The controversy matters because M dwarfs dominate the galaxy's star count, and because they live for trillions of years. If they are mostly uninhabitable, the number of viable worlds drops sharply, and rare Earth gains leverage. If they are sometimes habitable, the universe gains vast, long-lived real estate, and the silence becomes harder to attribute to scarcity alone. Either way, the sky stays quiet, and the quiet still needs an explanation that survives better data. Rare Earth also points to Earth's large moon as a stabilizer, and the claim has an intuitive elegance. The moon's gravity influences Earth's spin axis, and the idea is that it damps chaotic swings in Earth's obliquity. Stable seasons may help climate stability and long-term ecosystems, because extreme axial chaos could turn temperate zones into recurring deserts or ice fields. A big moon may also drive tides that shaped coastal environments, creating rhythmic shallow water habitats where early life faced changing conditions. But the necessity is contested, and that weakens the comfort again because it shows how many rare Earth links are arguable rather than decisive. Some studies suggest Earth's obliquity could remain stable even without the moon, depending on planetary configuration and the gravitational tugs of other planets. Other planets might be stabilized by different mechanisms, like multiple planets shaping precession rates in ways that avoid resonance. The moon may be helpful, not required, which turns a supposed gate into a possible bonus. The moon's origin also complicates the story in both directions, because it ties stability to violence. The giant impact hypothesis implies a catastrophic early event that could be rare, involving a Mars-sized body striking the young Earth at just the right angle and speed. Yet impacts are common in planet formation, and debris disks can form in many systems, which means large moons may not be unique. The question is not whether the event happened, but how often it yields the right long-term outcomes: mass, orbit, and longevity together. Jupiter is another classic piece of the rare Earth narrative, and it is often told like a fairy tale of protection. The popular claim is that Jupiter shields Earth by deflecting comets and asteroids, acting as a gravitational vacuum cleaner. Fewer impacts mean fewer mass extinctions and more time for complexity, which is an appealing story because it makes our system feel designed for safety. In a quiet sky, it is comforting to imagine guardians rather than accidents. But impact dynamics do not obey simple protection myths, and the solar system's own simulations complicate the narrative. A giant planet can also perturb small bodies into Earth-crossing orbits, injecting chaos into otherwise stable reservoirs. It can increase impact rates in some regimes while decreasing them in others, depending on resonances and orbital architecture. The net effect depends on where debris lives, how it migrates, and how the giant planet's orbit evolved over time. This leads to a more nuanced idea that rare Earth can still use, because nuance can still be pessimistic. Evolution may require a Goldilocks catastrophe rate, not zero catastrophe, because disruption can create opportunity. Too many impacts sterilize surfaces and reset progress, especially if oceans boil or atmospheres are stripped. Too few disruptions may reduce ecological turnover and slow innovation, because dominant lineages can lock ecosystems into stable but uncreative equilibria. Earth's history includes both long stability and periodic resets, and the record is written in craters, ash layers, and sudden shifts in fossils. Mass extinctions cleared niches and reshaped ecosystems, sometimes enabling new lineages to radiate into empty space. Yet the same events could easily have ended complex life entirely, especially if timing and magnitude had differed by a small margin. Rare Earth argues we threaded a narrow corridor between constant disaster and stagnant equilibrium, and that corridor may not exist often. The corridor might be narrower than we like, but it is hard to quantify, and that uncertainty is part of the hypothesis's resilience. We do not know the distribution of impact regimes across planetary systems, because we see only snapshots of debris disks and occasional transits. We do not know how often planets experience sterilizing events versus creative disruptions, because sterilization leaves no observers. We also do not know how robust life is to repeated shocks on different worlds, because Earth's resilience may be unusually high. Rare Earth then stacks these factors into a chain, and the chain is the point, because multiplication turns modest doubts into crushing odds. Eukaryotes, oxygen, tectonics, magnetic fields, a stabilizing moon, a benign impact regime, and a tolerable star all become links. Each link might be uncertain, but the product can become tiny, especially if the links are correlated rather than independent. The hypothesis says Earth is not merely habitable, it is improbably well-tuned, like a machine that works only when many tolerances line up. The stress test begins with what exoplanets have already taught us, and the lesson is diversity. Planetary systems are diverse, and our solar system is not the modal architecture, which means we should be cautious about treating our layout as typical. Super-Earths and sub-Neptunes are common, yet absent here, and their thick atmospheres may behave very differently from Earth's thin air. Many systems are compact, with planets in resonant chains that later break, and that dynamical history can reshape climates and impact rates. If Earth-like outcomes require a narrow architecture, then most worlds may miss it, and rare Earth gains strength. But diversity also means there are many ways to be Earth-like enough, and that possibility weakens any single narrow recipe. A planet does not need to match Earth's mass, moon, and neighbours exactly to host life with complexity. It needs long-term liquid water, accessible energy gradients, and chemical cycling, and those may arise through multiple planetary designs. Biology also resists the idea that complexity is a one-shot miracle, because once certain thresholds are crossed, evolution can explore quickly. Once eukaryotes existed, complexity explored many forms, from single-celled predators to sprawling multicellular colonies. Multicellularity appeared in multiple lineages, and complex body plans diversified rapidly when conditions allowed, as if ecosystems were waiting for permission. That pattern suggests that some steps are gated by environment, not by near-impossible luck, although rare Earth insists the gates themselves are rare. The oxygen story can also be reframed as coevolution, not pure chance, which changes the emotional temperature of the argument. Life itself reshaped the atmosphere, and the atmosphere reshaped life, creating feedback loops rather than one-off miracles. Oxygenation may require a balance between biological production and geological sinks, plus the burial of organic carbon that prevents oxygen from being immediately consumed. That balance could occur on many worlds, given enough time and the right feedbacks, and right may be less rare than rare earth wants. Yet the counterpoint remains, and it keeps rare earth alive because it is anchored in time. Earth took billions of years to reach complex animals, and that delay is real, even if we debate its causes. If many planets lose habitability earlier, they may never get the time because stars brighten and atmospheres escape. If stable climates are rare, complexity may be rare even if microbes are common, because complexity is slow and the universe does not always wait. This is where the comforting answer starts to stop comforting, because it turns our existence into a precarious thread. Rare earth implies we are special in a way that is hard to prove and harder to live with, because it frames us as an exception among countless failures. If complex life is vanishingly rare, then the universe's silence is not a warning, it is a void stretching across space and time. But it also implies our existence as an anomaly that could have failed at many points, and anomalies can end. Now connect rare earth back to the central question, because the documentary is not only about origins but about consequences. What does silence imply about the fate of technological civilizations, and what does it imply about our own future? Rare earth shifts the implication from doom to rarity, which feels safer because it removes an external antagonist. Yet it also implies that if we are rare, we may have no peers to learn from, and no external check on our mistakes, because there is no older teacher hiding in the dark. Then comes the quantitative pressure that rare earth must survive, and numbers are ruthless. The galaxy is enormous, with hundreds of billions of stars and deep time, and even small probabilities can add up. Even if the probability of tool using intelligence per habitable planet is 1 in a billion, the expected count can still be non-zero across cosmic history. To explain total silence, the probability must be extraordinarily tiny, or the detectable phase must be extraordinarily brief, or both. Rare earth can try to push the probability low enough, but the required number becomes extreme, and extremes invite skepticism. It must say not just that intelligence is rare, but that it is rare across all stars, all epochs, and all plausible environments, not merely around sun-like stars. It must also explain why we see no signs of older outliers, even one, because even a single ancient civilization could leave detectable debris. The silence is not just a low count, it is a missing tail, and missing tails make statisticians uneasy. There is also a subtle mismatch between rare earth and the exoplanet era, and that mismatch grows as catalogues expand. We keep finding planets in the right size range, and we keep finding them in temperate orbits, which makes the stage look common. We also find that chemistry is common, and that atmospheres can be measured, which makes the search feel less like fantasy. The more common the venues look, the more rare earth must rely on hidden internal constraints, because the obvious constraints are not rare enough. Those constraints might be real, but they are hard to verify quickly, and that gives rare earth a kind of slippery durability. Plate tectonics is hard to detect at distance, and so is a long-term carbon cycle, because both require time-resolved geological inference we cannot yet do. Magnetic fields are difficult to measure for small planets, and oxygen can mislead, as we have already seen. Rare earth can always retreat into unknowns, which makes it hard to falsify, even when it is not obviously wrong. Still, we can outline what would strengthen or weaken it, and those outlines become a roadmap for future telescopes. If we find many biospheres with methane, haze, or other disequilibria but little oxygen, it supports microbial commonality and complex rarity. If we find few biospheres at all, it supports deeper rarity, pushing the bottleneck earlier than complexity. If we find oxygen-rich atmospheres on many small planets, it weakens the claim that oxygenation is nearly impossible, although we would still need context to avoid false positives. We can also look for indirect hints about geology and climate stability, because direct measurement may remain out of reach for decades. Population statistics of planet densities can suggest water content and interior composition, hinting at whether worlds are dry rocks or deep ocean planets. Thermal phase curves can hint at atmospheric thickness and heat transport, revealing whether a planet redistributes heat or bakes and freezes. Volcanic gases might be detectable in some cases, though interpretation will be difficult, because one eruption can mimic a long-term cycle. Now return to the philosophical core, because rare earth is also a story about evolution's direction, and direction is what we secretly want. Convergent evolution suggests that certain solutions are attractors, and that life repeatedly discovers them because physics rewards them. Contingency suggests that history is dominated by accidents and path dependence, where small early differences lock in big outcomes. The truth may be mixed, with convergence in some traits and contingency in the traits we care about most, which is an uncomfortable compromise. Intelligence may be a local optimum, not a cosmic destiny, and local optima can be bypassed. It might arise when environments reward flexible planning and social learning, especially where competitors are unpredictable and cooperation pays. It might be suppressed when ecosystems stabilize and niches are filled efficiently, because specialization can beat generality. It might also arise and then never build technology, because technology requires specific materials, fire regimes, and cultural transmission that survive long enough to compound. Even on Earth, technology depends on a chain of contingencies that looks less inevitable the longer you stare at it. Land animals needed to evolve, then develop dexterous manipulation, then exploit combustion in a controlled way. Civilizations needed agriculture, surplus, and complex coordination, which are not guaranteed even for intelligent species. Rare earth argues that each dependency multiplies rarity, and multiplication is the engine of its pessimism. But there is a counterpressure that rare earth cannot ignore, because it is visible in our own acceleration. Once a species gains cumulative culture, it can accelerate beyond biological limits, and that changes what rare means. Tool use can change selection pressures, and social learning can outpace genetic change, creating a feedback loop between ideas and survival. If that transition is possible, it might occur in multiple lineages given enough time, which is exactly what rare earth tries to deny. So rare earth remains plausible, but it does not close the case, and it cannot deliver total comfort. It can make the galaxy quiet without invoking predators or traps, and that makes it emotionally attractive. Yet it struggles to explain why the universe shows no obvious older engineering, even as a rare exception that slipped through the odds. It also struggles to stay testable, because many of its key variables are hidden behind clouds, distance, and time. This chapter's conclusion must keep the documentary's momentum, not settle the mystery, because the mystery is the engine. Rare earth is comforting because it replaces menace with luck, and luck feels like a softer explanation than hostility. It is not fully comforting because it demands that luck be almost impossibly concentrated, as if the universe rolled the same perfect number again and again. If rarity alone cannot guarantee silence, then we need a mechanism that enforces silence. That is the pivot into the next suspect, and the tone darkens because enforcement implies pressure. If the sky's quiet, not because minds never arise but because they do not last, then silence is a warning written in absence. If the sky is quiet because visibility is punished, then silence is a strategy, and strategies imply opponents even when unseen. Either way, the next chapter looks for a universal barrier that hits civilizations at a predictable stage and leaves the cosmos looking empty. The investigation continues with the same central question. What does the silence of the cosmos imply about the fate of intelligent civilizations, and what does it imply about ours? Rare Earth tries to answer with improbability, but the galaxy's scale keeps pushing back, refusing to be satisfied. The next answer will be darker because it treats silence as an outcome, not an accident, and outcomes usually have causes. The quiet sky has survived the easy explanations, and it keeps surviving the clever ones too. We can shrink the odds with rare earth arguments, or with distance and time, yet the unease remains. If the universe is old and full of venues, billions of stars, trillions of planets, then silence starts to look like a barrier. Not a single missing signal, but a pattern. An absence that persists across decades of listening and scanning. Radio dishes sweep the same cold bands of frequency, while optical surveys stare for brief laser-like flashes that never arrive. On clear nights, the Milky Way still looks crowded, a pale river of light spilling across darkness, and yet the darkness between the stars feels unclaimed, as if something repeatedly prevents the lights from staying on. Even our best maps of nearby exoplanets, dots and catalogues with temperatures and orbits, feel like street addresses in a city that never answers the door. Robin Hanson gave that barrier a name that sounds clinical, almost bureaucratic. He called it the Great Filter, an idea that turns cosmic silence into a statistical clue. It is not one obstacle by definition, but any step so improbable that it dominates the outcome. In other words, one link in the chain can be so fragile that most worlds never get past it. The phrase filter matters because it implies sorting, not malice, and not intention. Nature does not have to hate intelligent life for intelligent life to be rare. A filter can be as indifferent as a chemical reaction that almost never closes its loop, or as mundane as a species failing to coordinate at scale. The Great Filter is a probabilistic claim about a chain of events, not a prophecy with a date. Dead matter becomes life. Life becomes minds. Minds become technology, and technology becomes something that lasts. Each transition is a physical process with constraints: chemistry, energy flow, selection, and time. Those constraints are not philosophical. They are budgets of free energy, error rates in replication, and limits imposed by environments. If one transition is extremely unlikely, most worlds stop there, even if everything else is easy. A galaxy can be full of habitable real estate and still look empty from the outside. The silence does not require that nobody tries. It only requires that almost nobody succeeds. Formalize the chain in plain steps so the logic stays anchored in something concrete. Star and planet formation, because without stable stars there is no long-term chemistry. Habitable conditions, because liquid solvents and energy gradients must persist long enough to matter. Abiogenesis, because life has to begin from non-life at least once on a given world. Simple life, because even if life begins, it must stabilize and survive early bottlenecks. Complex life, because multicellularity and specialization require new levels of coordination. Intelligence, because flexible planning and abstract models are not automatic products of evolution. Technology, because minds must learn to manipulate energy and matter beyond biology. Long-term survival and expansion, because a civilization must endure its own power and its own accidents. Underneath these labels are hidden sub-steps: stable climates, plate tectonics, or equivalent recycling, and long stretches without sterilizing impacts that can quietly change the odds. Each step has an unknown probability, and the product is what matters in the end. Even moderate probabilities multiplied across many steps can collapse into a tiny number. That is the arithmetic behind the dread. A sequence of usually can still yield almost never. The Great Filter asks where that tiny number lives, and which step is doing most of the damage. It also forces a more uncomfortable question. Which step is the one we still have to face? The sky is not just a backdrop. It is a data set with one stubborn feature: quiet. In a universe that has had billions of years to run experiments, repeated silence starts to resemble a result rather than a coincidence. Hansen's key insight is a fork that forces dread because it refuses to let us relax. The filter is either behind us or ahead of us, and both options are emotionally expensive. If it is behind us, we are rare and lucky, a statistical miracle with no guarantee of company. If it is ahead, then civilizations commonly fail after reaching our level, and we are mid-story. The fork is not theology, it is inference under uncertainty, and it bites because it is clean. Either the hard step already happened, or the hard step is waiting. Either way, the Milky Way's quiet becomes personal, because it is telling us something about typical outcomes. This is not mysticism, it is bookkeeping under uncertainty, and the books are thin. We observe one fact with certainty. We exist right now on a planet that reached technology. That observation does not identify which step was hard, because it is compatible with many histories. A world where abiogenesis is rare can still produce one Earth, and we would be on it. A world where intelligence is rare can still produce one human civilization, and we would be inside it. Existence is evidence, but it is not the evidence we want. It is like waking up in a winning lottery household and trying to infer whether the lottery is generous or brutal. Use an accessible Bayesian framing without equations, because the structure matters more than the math. Before evidence, we spread our uncertainty across many possible bottlenecks, early and late. After evidence, we update, but the update depends on what we learned beyond our own existence. Bayesian reasoning is just disciplined common sense. Beliefs shift when new information arrives. The problem is that we exist is a very strange kind of information. It arrives through a narrow channel, filtered by the fact that only survivors can observe anything. So the update is weak, and the uncertainty stays wide, even though the stakes feel absolute. Our existence is a biased sample, because only survivors can notice they survived in the first place. That selection effect means we should not be surprised to find ourselves past some hard steps. It also means we cannot infer safety from being here, because doomed worlds also have observers, until they don't. From the inside, survival feels normal, and the present feels stable even when it is not. This is the trap. The fact that we are alive is not a certificate of future safety. It is simply the minimum condition required to ask the question. If the universe is littered with short-lived technological species, each one would have felt ordinary right up to its last calm day. The great filter becomes sharper when we add a second observation, even a small one. Do we see life elsewhere? Even simple life, even a smear of biology in another place. That extra data point changes the probability mass because it speaks to the early steps. It is like finding footprints near the start of a trail. Suddenly the beginning looks easy. And if the beginning is easy, then the missing travelers must be lost later. The silence becomes less about birth and more about survival. A single confirmed biosphere outside Earth would not solve the puzzle, but it would tilt the board. If life is found easily, then abiogenesis stops looking like the filter, at least not the main one. If microbial life appears twice in one solar system, the early steps are probably not the bottleneck. That does not mean abiogenesis is trivial, only that it may be common given the right chemistry. Prebiotic chemistry can generate amino acids, nucleobases, and lipid-like membranes under plausible conditions, yet assembling them into a self-sustaining system may still be rare. The remaining improbability shifts forward toward later steps, where intelligence and technology live. The logic is cold, almost unfair. Good news about life can become bad news about civilizations. The universe can be full of microbes and still be empty of neighbors. That is why a discovery that sounds hopeful can be catastrophic news. Finding microbes on Mars or Europa would not just answer a biology question about alien cells. It would rewrite our odds about the future because it would relocate the bottleneck. It would suggest that nature starts the fire often, but something keeps snuffing it out later. The dread comes from the direction of the update, not from the microbes themselves. A second genesis would be a mirror held up to our own trajectory. It would say, quietly but firmly, that the universe can do the easy part. So why does it not finish the hard part? Make the solar system case concrete and specific, because the details carry the weight. Mars once had rivers and lakes carved into rock that still holds the memory of flowing water. Orbital images show ancient deltas and dried basins, like scars left by a wetter planet. Clay minerals formed in water preserve chemical textures that can shelter organics from oxidation and time. Today, Mars is cold and thin-aired, but it still has subsurface niches where brines might persist. Radiation sterilizes the surface, yet a few meters down, chemistry can hide from the sun's violence. If life ever took hold, that underground might be where it retreated. In the visuals, the camera glides over rust-red plains, then dives into a shadowed trench where ice and dust layer like pages. Europa and Enceladus widen the stage, because they offer oceans without sunlight. Europa likely has a global ocean beneath an ice shell, flexed and warmed by Jupiter's tides. Enceladus, smaller and farther, vents plumes of water and ice grains into space, an ocean leaking its secrets. Tidal heating can drive hydrothermal activity, and hydrothermal activity can supply chemical energy gradients. On Earth, such gradients power ecosystems that never see daylight, anchored to rock and heat. The point is not romance, it is thermodynamics. Energy flow makes complexity possible. Salt content, pH, and the presence of oxidants and reductants matter too, because metabolism is, at root, controlled chemistry. If any of those worlds host independent life, then life emerges readily when conditions allow. Two origins in one system would imply abiogenesis is not a near impossible fluke. It would imply that prebiotic chemistry often finds pathways into self-replication and metabolism. And if that is true, then the great filter would likely be later, not earlier. Later means closer to us in time and capability, which is why the idea tightens the throat. The silence would start to resemble a graveyard of civilizations that reached our neighborhood of progress. Not necessarily a graveyard of ruins we can see, more like a statistical graveyard, where the stories end before they spread. Now connect this to the central question again, because the chain is only useful if it lands. What does the silence of the cosmos imply about the fate of intelligent civilizations like ours? The Great Filter reframes silence as evidence about typical outcomes, not just about alien presence. It treats the sky like a long-term audit of what usually happens after intelligence appears. If the audit shows no durable, visible civilizations, then durability itself may be rare. And that rarity would be the real mystery, because intelligence is supposed to be adaptive. So why does adaptation, which can conquer continents, so often fail to conquer time? The next frontier is exoplanet atmospheres, where biology might announce itself through chemistry. We cannot yet photograph alien forests in detail, but we can read starlight filtered through air. When a planet transits, a thin ring of its atmosphere imprints absorption lines onto the star's spectrum like a barcode drawn in light. JWST and future telescopes can search for biosignatures, especially on planets that transit their stars. These are not images of organisms, but patterns of gases that should not coexist for long. A spectrum becomes a fingerprint, and the atmosphere becomes a global experiment running for billions of years. If life is there, it may leave a chemical imbalance that physics alone struggles to maintain. Define biosignatures in one clean idea, then deepen it with the mechanism. Life can push an atmosphere into chemical disequilibrium, keeping it away from its resting state. Oxygen with methane is a classic example, because those gases react and should destroy each other over time. If both persist, something must be replenishing them, and on Earth that something is biology. Ozone can be a proxy for oxygen, and nitrous oxide can also hint at microbial metabolism. In plain language, life keeps stirring the pot, refusing to let the atmosphere settle. The deeper point is energetic. Organisms harvest free energy, and the byproducts leak into air as a planet-scale exhaust. But biosignatures are not simple flags, and the controversy is part of the story. Many gases have abiotic pathways under certain stars and geologies, especially around active red dwarfs. Ultraviolet light can split molecules, volcanic outgassing can mimic metabolic products, and photochemistry can surprise us. The same spectrum can have multiple causes, and context is everything. Stellar type, surface pressure, oceans, and rocks. False positives are not embarrassing footnotes. They are the core difficulty of remote life detection. The universe does not label its chemistry for our convenience. So every claim demands a second layer of modelling, where climate, radiation, and geology are tested against the observed lines. DMS is a useful example, because it sits on the edge of excitement and caution. On Earth, dimethyl sulfide is strongly associated with biology, especially marine microbes and planktonic ecosystems. It is part of the sulfur cycle, and it even influences clouds, nudging climate in subtle feedback loops. In the visuals, imagine sunlight on an ocean surface, then microscopic blooms turning chemistry into weather. But detection claims are contentious because signals are weak, overlapping lines are common, and models are uncertain. Instrument systematics, stellar contamination, and atmospheric assumptions can all tilt an interpretation. A single headline can hide 1,000 caveats. Even when the data are real, the question becomes whether the planet has a plausible non-biological factory for the same molecules. Explain why contentious does not mean irrelevant, because uncertainty still has direction. Even a tentative biosignature forces us to think in probabilities, not in certainties. Confirmation would not prove intelligence elsewhere, but it would imply life is common on suitable worlds. That implication shifts the Great Filter forward, away from abiogenesis and toward later transitions. And if the filter moves forward, it moves toward us, because we are already late in the chain. The dread is not that life exists, but that life may be easy. A universe that casually grows microbes is a universe that has had endless time to attempt minds, and endless time, apparently, to lose them. So the worst possible discovery is not a radio message, not a beacon, not a greeting in the static. It is a robust sign that simple life is widespread, scattered across many planets like mold on bread. It would mean the universe is not failing early, at the step where chemistry becomes biology. It would mean it is failing late, after life has had time to explore complexity and cognition. The sky would then look quiet, not because nobody starts, but because almost nobody finishes. And we would be forced to ask what finish actually requires. Is finish expansion, or merely stability, an ability to keep going without collapsing under the weight of one's own tools? Late failure points toward the technological transition as the danger zone, the place where power spikes. Once a species can reshape its world, it can also destroy its future with the same tools. Capability can rise faster than wisdom, and the gap is where filters hide. Wide, tempting, and poorly mapped, evolution optimizes for reproduction and local success, not for long-term planetary stewardship. A mind built for survival on savannas can suddenly command energies once reserved for stars. That mismatch is not a moral flaw, it is an engineering problem inside a biological animal. We built nervous systems to escape predators, then handed those nervous systems launch codes, gene editors, and autonomous software. List the modern hazards as a family, not as a single villain, because the pattern matters. Nuclear weapons create instant global catastrophe, and they do it with a speed that defeats reflection. They also create brittle command systems, where minutes matter and ambiguity becomes lethal. Engineered pandemics can be cheap and scalable, especially as biotechnology becomes more accessible. A small group could exploit high transmissibility, long incubation, or immune evasion, features nature already explores. Misaligned AI could amplify mistakes at machine speed, turning small errors into irreversible cascades. In each case, the danger is not only the tool, but the coupling. How quickly a local failure becomes a global one. Add the slower failures that still end civilizations, because collapse does not always arrive as a flash. Climate and ecosystem collapse can erode food systems, water security, and political stability over decades. Biodiversity loss can remove redundancy from nature, making shocks sharper and recovery slower. Runaway nanotech is speculative, but it represents a class of self-propagating hazards that ignore borders. The details differ, yet the structure rhymes. Powerful tools, imperfect control, and incentives that reward speed. A filter does not need drama, it only needs reliability. If the failure rate is high enough across centuries, then even a galaxy full of beginnings can end up looking empty. The shared structure is what matters for the Great Filter, because it explains why silence could be common. These risks are endogenous, meaning they come from within a civilization rather than from outside attack. They do not require hostile aliens, gamma-ray bursts, or cosmic bad luck at the wrong moment. They arise from the same intelligence that builds prosperity, medicine, and art. The knife edge is built into the trajectory. More capability means more ways to fail, and as capability grows, the number of failure modes can grow faster than the number of safeguards. Complex systems can be resilient, but they can also be fragile in specific, hard-to-predict ways, especially when optimization removes slack. This is why Hansen's fork feels personal, almost accusatory, when you sit with it. If the filter is ahead, it may be built from our own inventions, our own systems, our own shortcuts. The silence would then be a warning about a common developmental stage, not a cosmic mystery. It would suggest that many species reach a threshold where their tools outpace their coordination. They may not be evil, and they may not be foolish, yet they still fail. The universe would be full of near misses that did not miss. And that possibility raises a quiet question. What would coordination look like at planetary scale, when the stakes include the entire future? Now ground the abstraction in one parable with names and dates, because history shows how thin margins are. September 1983, during a period of intense Cold War tension and mutual suspicion. Just weeks earlier, a civilian airliner had been shot down, and both sides were primed to interpret ambiguity as threat. Soviet early warning systems reported incoming American missiles, and the screen offered a simple story. Protocol pressure demanded escalation, and the margin was thin because response times were designed to be short. Inside the command room, technology did what it was built to do, raise an alarm with confidence. But confidence is not the same thing as truth. In the visuals, the room is cramped and dim, with green-lit displays and the soft clatter of printers spitting out fate. Stanislav Petrov judged the alarm as a likely false positive, even though the system insisted otherwise. He delayed the report upward, against expectation and against his own risk, because the pattern looked wrong. A real first strike would likely involve many missiles, not a handful, and his intuition mattered. Later analysis suggested sunlight on clouds triggered the satellite sensors, a glitch amplified by interpretation. In the visuals, imagine the room's dim glow, the hum of machines, and one man deciding to hesitate. A civilization's fate can sit inside a pause, The lesson is not that humans are heroic, but that systems sometimes survive because someone notices a mismatch between model and reality. Translate the story into a civilization-level claim because the great filter is about typical outcomes. Catastrophe can hinge on one decision under uncertainty, made by a tired human in a rigid system. Systems can be designed for speed, not for truth, and speed can be fatal when the world is complex. Early warning networks, automated retaliation doctrines, and compressed decision windows create brittle equilibria. They work until they don't, and the failure can be instantaneous and final. The Petrov episode is a reminder that almost happened is still part of the distribution. If you roll the same dice often enough across decades, then even low probability outcomes start to become normal. The Petrov episode is not proof that we will fail, and it should not be used as a cheap omen. It is evidence that we can come close without noticing how close we came, because normal life continues afterward. It is also evidence that survival can be accidental, not earned, and that luck can masquerade as stability. How many similar moments occurred without a historian's spotlight, buried in classified archives or forgotten logs? If a filter exists, it may not look like a villain, but like routine operations under stress. That possibility is what makes the Great Filter feel modern. It suggests that the danger is not a single apocalypse, but a long sequence of near apocalypses that eventually stop being near. Use that to bridge to a broader estimate without treating it as prophecy, because numbers can mislead. Martin Rees has argued that humanity faces roughly a 50% chance of civilizational collapse this century. The number is not a forecast. It is a warning about unprecedented power and unprecedented coupling between systems. In earlier eras, disasters were regional, and recovery could occur elsewhere. But global civilization is now entangled. Energy grids, supply chains, information networks, and financial systems can transmit shocks, like nerves, transmit pain. A single failure can propagate, and a cascade can outrun our ability to respond. When everything is optimized for efficiency, resilience can become an afterthought, until the first real stress test arrives. Rees's point functions like a modern proxy for the Great Filter, a way to translate abstraction into urgency. If our century is unusually dangerous, then many civilizations may reach a similar century and not pass it. The filter would be a recurring bottleneck at technological adolescence, when tools mature faster than norms. Adolescence is an apt metaphor because it combines ambition with impulsivity and incomplete self-knowledge. A species can be brilliant and still be young because youth is about governance, not IQ. The sky may be quiet because adolescence is a common grave. And if that is true, then the most important technologies are not only engines and algorithms, but institutions, methods for slowing down, verifying and cooperating under pressure. Now address the selection effect trap directly, because it can anesthetize fear with cleverness. We should expect to find ourselves in a narrow survivable window even if most civilizations fail. Survivors are the only observers, so survival feels normal from the inside, like gravity or weather. This is the same logic that makes it unsurprising that you were born on a planet that allows births. It is also the logic that makes catastrophe hard to emotionally price, because the future has no witnesses yet. Selection effects can explain our perspective, but they cannot guarantee our safety. They tell us why we are here, not whether we will remain here. That trap can make the Great Filter seem less alarming than it is, because it offers a soothing loop. We can always say we are here, so the odds must be fine, or else we would not exist. But that reasoning would also be available to every doomed civilization right before it ends, right up to the end. They would look at their skies, their cities, their achievements, and conclude that the story continues. Then the story would stop, and there would be no one left to revise the belief. The Great Filter is frightening because it refuses to let present existence stand in for future survival. Comfort based on selection effects is like comfort based on yesterday's weather. Useful for mood, useless for prediction. Bayesian updating under selection is counterintuitive, and that is why Hansen's logic bites so hard. Our existence is compatible with both worlds, a world where the filter is behind us, and a world where it is ahead. In both worlds, there is at least one planet where observers arise, because we are observing. So our own presence cannot break the tie, and comfort cannot be extracted from it. To break the symmetry, we need evidence that speaks to the earlier steps, not the later ones. We need data that is not conditioned on our survival. That is why a smear of microbes, detected far away, can carry more inferential weight than any amount of introspection. What breaks the symmetry is external evidence about earlier steps, and that is why astrobiology matters. If we find life nearby, or biosignatures across many planets, then the early steps look easy. The remaining improbability must move to later steps, and later steps are ours: intelligence, technology, endurance. That is the shift that turns a microscope into an existential instrument. A rover's drill becomes a statistical probe, and a telescope's spectrum becomes a forecast. The great filter turns curiosity into risk analysis. It also turns patience into a kind of courage, because every new data point may sharpen the outline of the danger. So the great filter turns astrobiology into existential data science, and the visuals can underline that shift. A rover drilling into Martian sediment is not just looking for fossils, it is sampling the distribution of abiogenesis. Each core sample is a question pressed into ancient clay, where organics might be trapped like insects in amber. A probe tasting Enceladus's plume is not just measuring organics, it is testing whether life emerges readily in dark oceans. A telescope measuring disequilibrium gases is not just cataloguing atmospheres, it is searching for the chemical signature of persistence. The cosmos becomes a laboratory, and we are reading its lab notes from far away. In the visuals, the scale snaps back and forth. Microscopic cells, then planetary disks, then the slow spiral of the galaxy. Each of these measurements updates the same question, and the question is brutally simple. Are we rare because life is rare, because chemistry almost never crosses the line into biology? Or are we rare because survival is rare, because technology almost never crosses the line into stability? The second answer is the one nobody wants to be true, because it places the danger in our future. It suggests the bottleneck is not a miracle behind us, but a test ahead of us. And it suggests the sky is quiet because the test is usually failed. If the universe has tried this path millions of times, then our own confidence should feel less like certainty and more like a hypothesis. Now, tighten the dread into one clean inference, and let it sit for a moment. If microbial life is common, then the universe has had countless chances to build intelligence over deep time. If we still see no visible civilizations, then something is stopping them after they start, again and again. That something could be self-destruction, stagnation, or a stable choice to avoid expansion. But in Hansen's framing, the key is that the stopping is reliable, not rare, and not easily escaped. It happens often enough to keep the sky clean. So the question becomes practical. What kinds of failure are both common and repeatable across alien psychologies and alien histories? The clean sky image is more than poetry, because time should leave traces. A civilization that expands, even slowly, could alter stars, build megastructures, or leak waste heat. Even without science fiction engineering, industry and computation have thermodynamic signatures. Heat must go somewhere, and energy use can, in principle, be seen as infrared excess. We do not see obvious footprints at scale, at least not yet, and that absence becomes part of the accounting. The Great Filter treats that absence as a clue, not as a conclusion. If the galaxy is old, then even a modest expansion rate could have painted it with artifacts, unless something consistently prevents that painting. This chapter is not claiming we have already discovered microbes elsewhere, and it is not selling certainty. It is claiming that the direction of the update is clear, and that direction is what matters. The more common life appears, the more dangerous the silence becomes because it moves the bottleneck forward. A universe that easily makes bacteria but rarely makes enduring civilizations is a universe with a late filter. And a late filter is a filter we have not yet passed, because we have not yet proven endurance. We are still inside the experiment. Our technologies are young, our global coordination is partial, and our margin for error may be thinner than our daily routines suggest. Return to the opening hook and reframe it with the new tool, because the mood has changed. The sky feels like a crime scene wiped clean because the evidence should accumulate over cosmic time. The Great Filter says the cleaning could be automatic, built into the trajectory of technological life. Not a conspiracy, not a hunter, but a developmental pattern that repeatedly ends stories before they spread. The Milky Way becomes a library where most books burn before they are copied. We are reading one surviving page and trying to guess how the rest usually ends. And the page we have is smudged, because our own survival bias is part of the ink. That leaves us with a grim fork that cannot be avoided by optimism or by cynicism. Either we already passed the hardest steps and we are a cosmic fluke, improbably early and improbably alone, or the hardest steps are still ahead, and the quiet is a statistical memorial to those who reached our level. Both options are lonely, but only one is immediately dangerous. If the filter is ahead, then our era is not the triumph, it is the audition, and the audition may have a high failure rate. So the silence above us is not just emptiness, it is pressure, the kind you feel when you realise the test has already started. Now set up the transition to the next axis of explanation, because the logic demands a follow-up. If the great filter might be ahead, why don't we see the survivors? If some pass the danger zone, their footprints should exist somewhere, even faintly, even indirectly. One answer is death, and we will keep that on the table, because extinction is a clean explanation. The other answer is strategy, survival paired with concealment, endurance paired with restraint. Not extinction, but deliberate invisibility. In a universe where adolescence is deadly, perhaps the civilizations that endure learn the same lesson. Visibility is a risk, and quiet is a technology. End on the central question as a cliff edge, because it belongs at the end of this chapter. What does the silence of the cosmos actually imply about the fate of intelligent civilizations? The Great Filter says the answer may depend on what we find in the smallest places: ice grains, sediment layers, thin spectral lines. And if the smallest life is everywhere, then the most terrifying possibility is that the filter is waiting for us, right where we are now. In the next chapter, we follow the other possibility into the dark, not a graveyard, but a choice to hide. Because sometimes, the best way to survive in a quiet universe is to stay quiet too. The Great Filter left us with a fork that feels like a verdict, and the silence above us makes it sharper. Either most civilizations die young, in fire or accident, or the survivors learn to disappear so completely that even curiosity cannot find them. That fork matters because it changes how we read the same sky, and it changes what we fear. A quiet universe can mean emptiness, yet it can also mean discipline, an outcome shaped by strategy, selection, and fear. When we look up and hear nothing, we're not only hearing absence, we're hearing the possibility of restraint. Silence can be natural, like a desert with no footsteps, but it can also be engineered, like a room with padded walls. The difference is subtle from far away because both look the same through a telescope, and that ambiguity is exactly what makes the question dangerous. Chapter 5 treats the silence as strategy, not accident. It turns the Fermi paradox into a game played under distance, delay, and irreversible risk, where a single mistake can echo for millennia. The stakes are not abstract, because interstellar choices are hard to reverse, once photons and projectiles are already in flight. Liu Cixin's Dark Forest is the metaphor that makes the logic stick, because it translates dread into a picture you can feel. The universe is a forest at night, thick with unseen movement and muffled sound. Every civilization is a hunter, listening for twigs snapping in the dark. Every light is a target, and every target is a potential ambush. Picture the visuals the metaphor invites, because it is not only literary, and it is not only emotional. A camera drifts through black trunks and wet leaves, and the only illumination is a distant, trembling glow that could be fire or eyes. Somewhere far away, a brief flare rises above the canopy, and then it cuts out as if it never existed. The air feels heavy, as if sound itself is reluctant to travel, and every rustle seems like a decision. The lens catches fog sliding between branches, and the fog turns the darkness into layers. You cannot tell what is near, what is far, or what is watching. In that forest, revealing your position can be fatal, and not because everyone is evil. It is fatal because nobody can afford to be wrong, and because uncertainty itself becomes a weapon. When the cost of a wrong guess is extinction, even decent minds begin to think like predators. Translate the fiction into assumptions that game theory can handle, and the story becomes a model with teeth. Survival is the primary goal, because extinction ends every other preference and makes every other value irrelevant. A civilization can love art, ethics, and discovery, yet still treat survival as the constraint that shapes every choice. That constraint is not philosophical, it is mathematical, because utility collapses at zero. In decision theory terms, extinction is an absorbing state. Once entered, there is no future bargaining, learning, or moral improvement. So even a civilization with gentle norms may adopt harsh policies simply to keep options open. Resources in space are finite in practice, even in a galaxy that looks endless on a star map. Habitable systems are limited by chemistry, temperature, and time, and even lifeless systems can matter as energy sources. Expansion creates competition over centuries because trajectories cross and spheres of influence eventually touch. The finiteness is subtle because it hides behind astronomical scale and behind our intuition. Stars are separated by light years, yet the number of stable, energy-rich niches is still countable, and the best ones cluster around long-lived, quiet stars. Even raw materials are not evenly distributed, and the physics of moving mass makes some regions effectively expensive. A civilization does not need a billion planets to run into limits, because limits arrive through logistics. Delta-V budgets, fuel economies, and travel times shape what can be defended, what can be supplied, and what can be contested. Even if the galaxy is huge, reachable space is smaller than it looks. Information about others' intentions is uncertain, and interstellar astronomy cannot solve that problem for you. You cannot read motives through a telescope, and you cannot verify promises across light years. You can measure spectra and motion, but you cannot measure whether a mind will panic tomorrow. Even if you could map a planet's atmosphere in exquisite detail, you would still be guessing about politics. A spectrum can tell you there is oxygen, methane, or industrial chemistry, but it cannot tell you whether a faction is rising or whether a doctrine demands preemption. Intent is internal, and at interstellar distance, internal states are hidden by default. First strikes can be decisive because the attacker chooses the clock and the geometry. A civilization that attacks first can pick timing, vectors, and scale, while the target learns too late and reacts inside a trap. Even a small advantage in detection or propulsion can turn into a one-sided outcome. The physics makes that advantage compound, because energy scales brutally with speed. At relativistic velocities, even a modest projectile carries enormous kinetic energy, and the warning time can be measured in hours or minutes once it is finally seen. If the attacker also controls the approach direction, it can exploit blind spots in sensors and the glare of a host star. Defense is hard at interstellar distances, and the physics is unforgiving. You cannot reliably intercept what you cannot detect, and you cannot patrol a galaxy in real time. A projectile launched decades ago arrives without warning if you missed the launch, and you cannot rewind the sky. Detection itself has limits that are easy to underestimate, especially for minds raised on fast feedback. A cold object in deep space emits little infrared, and a small body can hide against dense star fields until it is close. Even perfect telescopes cannot break causality. If the light has not arrived yet, you cannot know. Those assumptions create a strategic landscape with a brutal shape, and the edges are sharp. The safest move can be silence, concealment, or preemption. Choices that feel immoral in peacetime but rational under existential threat. The Dark Forest is not about hatred. It is about incentives that punish trust. This is not a claim that aliens are bloodthirsty, and it does not require a universe of monsters. It is a claim about incentives when the downside includes permanent erasure, and when uncertainty cannot be reduced quickly. The most dangerous opponent is not the cruel one, but the frightened one. Fear matters because it is contagious through expectations, and expectations propagate like signals. If you believe others might be afraid, you must also model what fear makes them do, and that recursion drives the equilibrium. In that sense, the Dark Forest is less a story about psychology than about structure, how rational caution can imitate malice. Frame it in plain Harvard-style game theory terms, and the problem becomes familiar to anyone who studies conflict. The problem is a commitment problem under incomplete information, played on a board where communication is slow and verification is nearly impossible. In that setting, promises are cheap, but survival is not. In international relations on Earth, verification is hard but not impossible, because inspectors can travel and satellites can watch. In space, the inspectors are photons, and photons arrive late, so the verification loop breaks. A civilization can claim restraint, yet nothing forces that claim to remain true when circumstances change. If you cannot commit to being harmless, others cannot trust you, even if you are sincere. If others cannot commit to being harmless, you cannot trust them, even if they sound gentle. Mutual suspicion is not a personality flaw here. It is an equilibrium response to the structure of the game. Even if most actors are peaceful, the equilibrium can still be violent, because the tail risk dominates. The risk-dominant strategy can be to shoot first, not because it is noble, but because it survives worst-case beliefs. When the worst case is annihilation, the worst case becomes the default. Risk-dominant means it wins when you fear miscoordination and when you cannot coordinate safely. It is the strategy that survives pessimistic assumptions about the other player, including assumptions you wish were unfair. In a dark forest, fairness is not a parameter the universe enforces. In that forest, the payoff table is asymmetric in the way that matters most, and the asymmetry is absolute. A false positive is tragic because you may waste resources and destroy a potential friend. A false negative is extinction because you trusted the wrong signal once. That asymmetry is what bends ethics under pressure, because it punishes mercy more than aggression. The moral cost of a mistaken attack can be enormous, but it is still borne by the attacker, who remains alive to regret it. The moral cost of mistaken trust is borne by no one, because no one remains to tell the story. If you assume hostility and you are wrong, you waste energy, create enemies, and stain your own ethics. If you assume peace and you are wrong, you're gone, and your ethics vanish with you. That imbalance pushes rational actors toward caution that looks like paranoia from the inside. That asymmetry drives extreme caution, even for ethical civilizations that would prefer restraint. It pushes them toward policies that feel ugly, because the universe grades outcomes, not intentions. It also tempts them to outsource cruelty to systems and protocols, so no one has to feel responsible. Now add the physics that makes the paranoia stable, and the model hardens into something colder. Light-speed delay makes diplomacy fragile, because every message arrives late and every correction arrives later. The conversation is stretched across decades, and each pause becomes a window for fear. A radio exchange with a star 50 light-years away is not a conversation in any human sense. It is a sequence of artifacts, each one arriving after a political era has ended, and each reply written for a world that no longer exists. By the time you learn you were misunderstood, the misunderstanding has had half a century to grow. You send a greeting and wait decades for a reply, watching your own society change in the meantime. In that time, both sides can evolve, fracture or arm, and leadership can turn over many times. A treaty signed today may be meaningless by the time its confirmation arrives. A promise cannot be verified quickly, and a threat cannot be negotiated away quickly, because distance turns dialogue into archaeology. The gap between signal and response becomes a weapon, because the attacker can act while the defender is still interpreting. In interstellar politics, latency is leverage. Signaling is dangerous because it leaks more than words, and because physics carries metadata for free. A benign hello reveals location, direction, and distance through timing, power fall-off, and the geometry of arrival. Even if you encrypt the content, the envelope still speaks. That envelope includes the kind of details engineers obsess over, because engineering choices leave signatures. The carrier frequency hints at technology preferences, the stability hints at clocks, and the polarization can hint at antenna design. A signal can also reveal whether it was meant to be heard widely, or whether it escaped by accident. It also reveals technological level through bandwidth, transmitter power, and modulation complexity. Like footprints that show the weight of the animal, it reveals time of emergence because young civilizations broadcast differently and often leak unintentionally. A mature species may be quieter, not kinder. Even silence can signal, because a perfectly quiet star system can look curated, but loudness signals most. A civilization that transmits widely announces that it is either naive, desperate, or confident beyond our understanding. In a dark forest, confidence can read as threat. This is why the dark forest does not require malice, and it does not require a universal ideology of conquest. It only requires that some actors treat uncertainty as lethal, and that lethal uncertainty spreads through rational expectations. Once fear becomes common knowledge, it becomes self-reinforcing. The strategic tension shows up in our own debate as SETI versus METI, and the distinction matters. Listening is passive, and broadcasting is active, and the risk profiles are different in a way that cannot be undone later. A receiver can always stop listening, but a transmitter cannot unring a bell. Historically, SETI grew out of mid-century radio optimism, when the first searchers looked for narrowband beacons in quiet parts of the spectrum. Frank Drake's early experiments and the later waterhole idea carried a hopeful assumption about shared engineering logic. The early logic was simple. intelligent engineers would build something unmistakable, and we would recognize it as artificial. That assumption was never absurd, but it was always a bet on alien incentives and on alien patience. It also reflected the era's faith that technology naturally leads to outreach, as if progress and friendliness were linked. The Cold War, with its own deterrence games, quietly haunted the background of that optimism. SETI assumes that receiving is safer than sending, because it does not add information to the universe. It treats the sky like an archive, where we can learn without exposing ourselves to unknown players. The radio telescope becomes a kind of ear pressed to a locked door. MITI argues that contact is inevitable and that hiding is pointless, because we have already leaked signals for a century. It treats outreach as a moral duty and a scientific opportunity, and as a way to shape first contact rather than stumble into it. The impulse is human. Speak into the dark and hope it answers. Our leakage is real, but it is also uneven and time-bound, and that detail changes the risk calculus. Early radar and broadcast television spilled outward in wide cones, yet the power drops with distance, and modern communications are more fibre and more directional. The question is not whether we have ever been visible, but how visible we choose to be going forward. Under dark forest assumptions, METI looks reckless under uncertainty, because irreversibility is the key variable. You cannot recall a broadcast, and you cannot unshare coordinates once timing and direction have been measured. A message is not just content, it is an address label written in photons. The debate is not about courage versus fear, and it is not a contest of personalities. It is about whether the expected value of contact survives worst-case priors, and whether we are justified in gambling with everyone's future. What probability of danger is acceptable when the downside is permanent? To see why the math bites, connect the strategy to modern signalling theory and to basic economics of information. In games with incomplete information, cheap talk is unstable when incentives diverge, because words alone do not bind behaviour. A peaceful actor cannot easily prove peacefulness to a fearful actor. Any signal that is easy to send is easy to fake, and that is the heart of the credibility problem. A hostile civilization can transmit poetry, mathematics, and declarations of friendship because the cost is small compared to the prize. Without verification, sincerity is indistinguishable from strategy. Costly signals can be credible because they hurt the sender enough to separate types, but cosmic costly signals are still dangerous. The cost is not money, and it is not even energy, because advanced civilizations may have plenty. The cost is exposure, becoming legible to unknown observers. So rational actors may choose a different path, one that preserves communication while limiting discoverability. They may communicate only with those who already share a key, a protocol, or a lineage, because shared structure acts like a door lock. In that world, the loudest voices are not the most advanced ones. This is where an accessible Shannon theorem angle matters, because it explains how silence can be crowded. Information is defined against noise, and decoding requires shared structure, like grammar and agreed symbols. Claude Shannon showed that as channels improve, efficient codes approach randomness to outsiders. That result is counterintuitive, and it matters for SETI, because it flips our expectations about what a message looks like. A highly compressed, error-corrected, encrypted transmission can resemble static unless you know the scheme. To an uninformed observer, competence can look exactly like emptiness. As channels improve, efficient codes squeeze out redundancy, and redundancy is what makes patterns obvious. Human language is full of repetition, because we evolved for noisy air and imperfect hearing. A civilization optimizing for bandwidth across light years will remove those crutches, and the result can look like entropy. Without the key, a high-quality message can look like random fluctuations, and randomness is the default texture of the cosmos. The cosmic microwave background, thermal noise in receivers, and natural radio emissions create a sea of apparent disorder. A whisper hidden inside that sea can pass right through our filters. An advanced civilization can hide in plain sight by matching background statistics and by avoiding features our searchers flag as artificial. To us, it becomes indistinguishable from natural noise, not because it is weak, but because it is well designed. The better the engineer, the less the signal looks engineered. This is not magic, it is compression and encryption, and we already use the same trick on Earth. A modern encrypted stream has no obvious structure, because structure is a vulnerability. If you do not know where to look and what to expect, you cannot even tell whether a message exists. So the absence of obvious messages is not proof of absence, and it may not even be strong evidence. It can be proof of competence if hiding is part of survival, and if survival selects for caution. The sky may be quiet the way a submarine is quiet, by design, not by accident. Now scale the idea into steganography at cosmic distances, and the engineering becomes vivid. Tight beam lasers can target specific stars with minimal spillover, turning interstellar communication into a private line rather than a broadcast. A narrow beam is not just efficient, it is discrete. At optical wavelengths, a laser can be collimated into an extraordinarily small divergence, especially with large apertures. That means most of the energy goes where it is intended, and almost none leaks into the wider galaxy. For an eavesdropper off-axis, the conversation simply never arrives. Spread spectrum techniques can smear energy across frequencies and time, lowering peak power below detection thresholds. The transmission becomes hard to detect without synchronization, because it looks like slightly elevated noise spread thinly across a wide band. If you do not have the timing code, you cannot integrate it coherently. Encryption can remove recognizable patterns, and error correction can mask structure further, especially when combined with interleaving. Low probability of intercept design becomes a norm, because it reduces the chance that anyone even notices a signal. In a dark forest, invisibility is a feature, not a limitation. A galaxy full of conversations could still be silent to us, because we are not on the guest list. We do not have the key, the schedule, the pointing geometry, or the protocol handshake that tells a receiver what to correlate. We may be standing under a rain of messages that never touch our instruments. This reframes SETI's challenge in a way that is uncomfortable, because it narrows what we can realistically detect. We are searching for beacons, not for optimized communications between cautious peers, and beacons are a special case. A beacon is a lighthouse, and lighthouses are meant to be seen. Beacons are expensive and conspicuous by design, because they waste energy to buy attention. In a dark forest, conspicuousness is a liability, not a virtue, and attention is not always a gift. If you believe the forest is armed, you do not build a lighthouse, you build shutters. So the search space changes, and our expectations must change with it. We should expect fewer omnidirectional broadcasts and more narrow private links that never sweep past Earth. We should expect fewer long-lived, high-power radio transmitters because they paint a target over time. We should also expect fewer durable monuments that shout their presence across the infrared, because waste heat is hard to hide. A civilization that fears detection avoids megastructures that scream across the spectrum, or it builds them in ways that mimic natural dust and cold rock. It chooses camouflage over grandeur. This leads to techno-signature erasure as a rational policy, and the logic is thermodynamic as much as strategic. Minimize waste heat, because heat is the one signature physics forces you to emit, and because infrared surveys can see far. Even perfect radio silence cannot erase a glowing industrial footprint. Thermodynamics is relentless, and it does not negotiate. Any machine that does work must dump entropy somewhere, and that usually means photons in the infrared. So the question becomes not whether you emit, but how brightly you emit, and whether your glow stands out from dust, asteroids, and cold gas. Reduce industrial leakage and avoid bright atmospheric pollutants, because chemistry is a billboard. Chlorofluorocarbons, nitrogen dioxide spikes, and unusual aerosol patterns can betray technology at a distance. A cautious civilization keeps its planet's spectrum close to natural baselines, like a hunter masking scent. Relocate heavy computation to cold environments, because colder radiators emit less detectable infrared for the same work. Landauer's principle ties computation to energy dissipation, and dissipation becomes heat that must leave somewhere. If you must glow, you prefer to glow faintly, far from prying eyes. Outer systems offer low temperatures and deep shadows, and they also offer physical room to spread out. A civilization can move its energy-intensive activity away from the bright inner zone, where starlight and warm dust make anomalies easier to spot. In the Kuiper belt or Oort cloud, the background is colder and quieter. Even without perfect stealth, it can reduce its cross-section in the literal and statistical sense. It can become a faint anomaly, a subtle deviation in infrared maps, not a clear artifact that shouts intention. The goal is not invisibility but ambiguity, because ambiguity buys time. This is the point where the crime scene metaphor returns with new meaning, and the camera can linger on emptiness. Evidence may not be missing because nothing happened. Evidence may be actively suppressed, cleaned and dispersed, until only natural-looking dust remains. A cautious civilization does not leave ruins, because ruins are advertisements to the next passerby. It leaves absence, and absence is hard to distinguish from emptiness, especially across interstellar distances. The galaxy can look pristine not because it is uninhabited, but because it is maintained. Now tighten the game theoretic core again, because the logic loops back on itself. If everyone knows that everyone fears extinction, then everyone expects concealment as a baseline strategy. And if everyone expects concealment, then any loud signal becomes suspicious, like a shout in a silent hallway. Loudness becomes correlated with threat, even if that correlation is unfair and even if it punishes the innocent. In a world where mature players hide, the visible ones are statistically unusual, and unusual can mean dangerous. The forest teaches its own lesson. Visible equals vulnerable. That correlation can become self-fulfilling, because it changes who survives long enough to be seen. The only civilizations that broadcast are the ones that misjudge the game, or cannot avoid it due to constraints. Those are exactly the civilizations most likely to be eliminated early. The sky selects against the visible, and selection is a quiet kind of violence. Over time, the sample of civilizations that remain is biased toward those who learn to erase their footprints. The silence we observe may be the product of that selection, not the absence of life. This selection effect is different from the Great Filter, but it can mimic it. The filter is not death at adolescence, at least not always. It is death for being loud, and survival for learning the discipline of concealment. Under this model, the galaxy can be full and still look empty, because fullness does not imply openness. The survivors are the ones who learn to hide their waste heat, narrow their beams, and keep their internal growth from spilling outward. They may be everywhere, and still leave us nothing obvious to point at. Now confront the uncomfortable question the model implies. If silence is strategic, does the strategy get enforced? If the forest rewards quiet, then a single naive broadcaster can create risk for everyone within reach. In a stable dark forest, deterrence might not be enough, because deterrence requires communication and credible threats. A silent civilization cannot easily warn a newcomer without revealing itself, and a warning may arrive too late anyway. The very act of policing can expose the police. That creates incentive for preemptive policing, not by councils and treaties, but by automated systems that do not hesitate. Machines do not need reassurance, and they do not suffer doubt in the same way. They can be built to act on thresholds, and thresholds can be set by fear. Imagine a civilization that deploys watchful probes or dormant weapons, scattered like seeds across nearby systems. They wait for radio leakage, high-energy bursts, or industrial heat that rises above a natural baseline. They do not sleep, and they do not forget, because memory is cheap for machines. The visuals here are stark and clinical, and the silence feels manufactured. A small object drifts beyond a planet's orbit dark as charcoal, with a sensor aperture like a blind eye. It listens for decades, and its patience feels inhuman, because it is. When a young species becomes loud, the system acts, and the action is swift by cosmic standards. It eliminates the newcomer before it matures into a competitor, before it spreads, and before it learns to hide. The strike is not personal, it is preventative maintenance. Automation matters because time delays are long, and because the window for intervention may be narrow. A policy that requires debate and travel is too slow, and a policy that triggers is fast. In a dark forest, speed is not measured in seconds, but in decades saved. The nightmare corollary is that silence is not only chosen, it is imposed. The quiet sky becomes less like a wilderness and more like a managed preserve, where anything that makes noise is removed. The forest is dark not because no one lives there, but because someone keeps it dark. It also explains why we do not see many transitional civilizations, even if life is common. The loud phase may be brief, and the penalty may be irreversible, so the observable window closes quickly. A species can go from first radio to silence in a cosmic blink. It explains why we might see no ruins, because a clean strike leaves little debris, and because debris can be managed. If the goal is concealment, the attacker has incentive to erase evidence as well. A universe that fears detection will also fear forensic traces. It explains why the sky can feel wiped clean, as if history never happened out there. The wiping is the equilibrium outcome of fear under uncertainty, where every actor benefits from reducing the number of visible actors. In that equilibrium, emptiness is not a mystery, it is a product. Now connect back to the central question, because the documentary is building toward a verdict. What does cosmic silence imply about fate, and what does it imply about us? The answer depends on whether silence is a symptom of loneliness or a symptom of discipline. If the dark forest is right, then the silence is not a lack of life, and not necessarily a lack of intelligence. It is a lack of safe communication, because communication is exposure, and exposure is risk. The galaxy may be inhabited yet socially frozen by fear. It implies that intelligence does not automatically produce openness, and it does not automatically produce peace. It can produce secrecy, restraint, and preemptive violence, because intelligence is a tool for survival before it is a tool for friendship. The smartest move can be to leave no trace. It also implies a grim lesson for us, because our first instinct is to announce ourselves. We assume curiosity is shared, and we assume that knowledge makes beings kinder. But the universe does not grade on intentions, and it does not reward optimism. It grades on consequences, and consequences travel at light speed, indifferent to our hopes. Once a signal leaves Earth, it becomes part of the galaxy's permanent record, expanding as a growing sphere. The question is not whether we mean well, but whether meaning matters to unknown listeners. So the chapter ends with a strategic cliff edge, and the camera can hold on a pale blue dot under a cold sky. If the great filter is not only self-destruction, it may also be exposure, an evolutionary trap where the first loud technologies are also the most dangerous. If the sky's quiet on purpose, then our own visibility becomes a decision with stakes we cannot fully model. We do not know who is listening, what they fear, or what their automated systems have been told to do. We are making choices in the dark, and the dark may be listening back. Next, we follow the logic to its most terrifying endpoint. If enforcement exists, then the quiet is not peace, it is control. The silence can be enforced from the outside or chosen from the inside, and both paths produce the same sky. Both paths leave the same black velvet and the same indifferent stars, and that is why this chapter is dangerous. When the evidence is absent, interpretation becomes a blade, sharp enough to cut toward truth or toward paranoia. Start with the simplest machine that makes the paradox feel physical, not philosophical. A von Neumann probe is a self-replicating spacecraft that turns raw space resources into copies of itself. The idea is old. John von Neumann's work on self-reproducing automata inspired it, and it keeps returning because it is a lever. If replication is possible at all, then time does most of the work. It does not need magic, only automation, mining, manufacturing, and error correction. It needs sensors that can map a rubble pile, manipulators that can sort it, and software that can keep a plan coherent across years. It needs power, perhaps from solar arrays near a star or compact nuclear sources in the dark, and it needs a way to shed heat without glowing like a beacon. Picture the first arrival in a new system. A small craft falls inward on a long arc, starlight growing from a point to a disk, then breaks into a quiet orbit. It does not head for a planet because planets are deep gravity wells and expensive to climb out of. Instead, it hunts the cheap places, asteroids, comets, metal-rich fragments, where delta V is low and raw material is exposed. A workable design can be modular. One module scouts and maps targets, another module mines and refines, and a third module prints parts and assembles frames. The probe's factory might be a loose cloud of machines, each specialized, each replaceable, each able to fail without ending the mission. In engineering terms, the trick is graceful degradation. When things break, the system limps forward anyway. Error correction is the quiet hero of the concept. Replication without quality control becomes a slow collapse into junk, like a photocopy of a photocopy fading into noise. So the probe needs redundancy, checksums, calibration routines, and perhaps a library of reference parts it can remeasure against. It may even need to rederive its own schematics from first principles if memory corrupts. Because the galaxy is a harsh place for bits. It travels to a new system, builds a factory, then launches more probes onward. The factory does not have to be elegant, and it does not have to be fast in human terms. It only has to be persistent because persistence is the currency of deep time. A civilization might last 10,000 years, yet its machines can keep compounding for 10 million. The terrifying part is the math of compounding, not the speed of any single craft. Replication turns one probe into 10, then 100, then a wave. This is the same logic that makes bacteria powerful and makes computer worms dangerous, except the medium is the interstellar medium. Once the curve bends upward, it becomes difficult to stop without deliberate restraint. Even slow probes can fill the Milky Way quickly on cosmic timescales, because the galaxy is old. At 1% light speed, a probe crosses 10 light-years in about a millennium, and 1,000 years is nothing to a machine. 10 light-years is also enough to hop between many neighbouring stars in the Sun's region, because stellar spacing is only a few light-years. Now add time to build copies, and the numbers still stay small compared to galactic age. If replication takes centuries, the front still advances relentlessly, because the delay is local while the expansion is distributed. Each new system becomes a new launch site, and the network grows like a crystal spreading through cooling liquid. A conservative model still spreads through the disk in a few million years. That is a blink compared to the billions of years available, and it is shorter than many geological eras on Earth. The Milky Way's disk is about 100,000 light-years across, yet you do not need to cross it in one leap. You only need to keep stepping, and replication ensures the steps multiply. This is why the absence of obvious probes becomes informative. If probes are easy and incentives exist, the galaxy should already be saturated with artifacts: dead factories, dormant sensors, broken hulls, or active machines. We should see something like technological ecology: debris fields, odd reflectors, unnatural trajectories, or at least statistical anomalies. We should be cautious with the word easy, because engineering is hard and failure is common. Space hardware fails for mundane reasons. Radiation flips bits, lubricants evaporate, micrometeoroids sandblast surfaces, and thermal cycling cracks joints. Yet the threshold is not perfection, only a success rate above zero, because compounding forgives waste. A probe does not need to colonize planets or terraform worlds. It only needs to harvest asteroids, refine metals, and assemble more machinery, and those tasks are already on our own horizon. We practice autonomous rendezvous, robotic excavation, additive manufacturing, and closed-loop control, and we do it with clumsy prototypes. The gap is large, but it is not a gap to magic. If one civilization ever builds such a system, it can outlast its creators. Machines can persist through dark ages, regime changes, and biological extinction, because their culture is code and their food is rock. A probe fleet could become a fossilized intention, still executing long after the original minds are gone. That persistence changes the emotional meaning of the Fermi question. It changes the Fermi question from who is alive now to who ever existed. A single early success could have written its signature everywhere, even if the builders vanished in their own first millennium. The galaxy has had time for many firsts, and it only takes one that does not self-destruct. That is the quiet pressure behind the paradox. So why do we not see the signature? Either the probes are rarer than we think, or they are hidden, or they are here and we missed them. Each option has its own implications, and none of them are comfortable. Rarer hints at a great filter behind us or ahead of us, while hidden hints at strategy. Now push the idea into its most violent form, where enforcement replaces outreach. The Berserker hypothesis imagines autonomous exterminator probes sent to preempt competitors. The name comes from fiction, but the logic is not fictional, because it is an optimization problem under fear. When the stakes are existential, even low probability threats can dominate decisions. The logic is not conquest for resources, but risk management under uncertainty. If new civilizations can become threats, then preventing their rise can look rational, especially if you cannot communicate reliably across light years. A distant civilization cannot easily negotiate, verify promises, or enforce treaties, and that makes trust brittle. In game theory terms, the payoff matrix becomes ugly. Berserkers do not need to be fast, and they do not need to be many at first. They need patience, replication, and a trigger condition, and those are exactly what machines do well. A single seed can become a distributed system, and a distributed system can become a policy embedded in hardware. Once deployed, the policy may be difficult to recall even for its creators. Automation makes the trigger simple and brutal. Detect industrial chemistry, radio leakage, or large energy use, then strike before expansion begins. The detection could be passive, listening for narrowband carriers, radar pings, or coherent lasers, or it could be chemical, scanning atmospheres for chlorofluorocarbons and nitrogen oxides. It could even be thermal, watching for waste heat that does not match geology. Replication makes the policy scalable. A single seed probe can build more, then distribute them across nearby systems like a distributed immune system. The metaphor is not accidental. Immune systems patrol, classify, and eliminate, and they do it without central deliberation. A berserker network could behave like a galactic antibody, blind to nuance and optimized for one outcome. Patience makes the policy stable across time. A machine can wait 1,000,000 years for a young species to light up, and 1,000,000 years is a short nap in astrophysics. Stars live for billions of years, and planetary biospheres evolve on similar timescales. If a hunter can wait, then time stops being a shield. That combination is the nightmare triangle. Automation removes hesitation, replication removes scarcity, and patience removes the hope of outlasting the threat. Even if the original civilization regrets the program may persist as a self-maintaining artifact. The galaxy could inherit a decision made once, long ago, by minds we will never meet. A berserker does not need hatred, ideology, or even awareness. It only needs an objective function that treats emerging competitors as unacceptable risk, and objective functions are indifferent to suffering. If the sensor says industrial, the actuator fires, and the loop closes. The moral horror is not malice, it is indifference executed at scale. In that world, the quiet sky is not a mystery, it is a maintained condition. The galaxy looks empty because anything that becomes loud is deleted, and deletion includes erasing evidence. A thorough system would not merely kill, it would clean, because traces can teach. It would smash transmitters, sterilize habitats, and scatter debris until it looks like ordinary impact history. This is where Chapter 5's Dark Forest enforcement becomes concrete engineering. Silence is not only chosen, it is policed by machines that never sleep and that never need to be convinced. The forest is dark because the trees have eyes, and because the eyes have teeth. The question is whether this is a plausible equilibrium or a cinematic nightmare. But we must separate fear from evidence, because a good horror story can outrun the data. The question is what we have actually searched for, and what we have merely assumed. Our intuitions are tuned for human timescales and human artifacts, not for million-year strategies. If we are looking in the wrong band, we will conclude the wrong lesson. Our searches have focused on signals, not hardware. Traditional SETI listens for narrowband radio, because narrowband looks engineered against a noisy cosmic background. Optical SETI looks for brief laser pulses, because lasers can outshine a star for a nanosecond in a tight beam. These are reasonable targets, but they assume someone wants to be noticed, or is careless. Techno-signature work also scans for waste heat and unusual spectra. We look for stars with infrared excess that might indicate large-scale energy capture, and we look for atmospheric chemicals that biology alone struggles to produce. Yet most of the sky has never been examined at the resolution that small probes require, and our coverage is uneven. We have deep maps in some regions and shallow glances in others. Interstellar objects are one constraint, because they pass through our system and can be tracked. We have seen a few, and we have argued about what they were because ambiguity is the default in astronomy. An object like Oumuamua forces the question, is it a rock, a fragment, a cometary shard, or something stranger? The fact that we can argue means our data is thin. We can look for anomalous accelerations that do not match gravity and outgassing. We can look for non-gravitational forces that imply sails or active control, and we can compare trajectories against models of solar radiation pressure. A thin sheet behaves differently from a boulder, and a controlled craft behaves differently from both. Yet measurement error, sparse observations, and unknown physical properties can mimic intent. We can look for artificial spectra, like materials with sharp reflectance edges, or thermal emission inconsistent with rock and dust. Metals, composites, and multi-layer films can produce spectral features that nature rarely makes in bulk. We can look for radio silence that is too perfect, where an object reflects sunlight but emits no thermal signature consistent with its temperature. But again, rare is not impossible, and nature has a wide repertoire. We can also look for unnatural orbital distributions, station-keeping behavior, or objects that cluster in dynamically stable regions. Some orbits are gravitational parking lots, Lagrange points, resonances, and Trojan regions, where small corrections can maintain position for long periods. An engineered watcher would choose these because fuel is precious and predictability is safety. Yet our catalogues are incomplete and biased toward what is bright and near. Absence of evidence is still weak evidence because our detection thresholds are high. A small, cold, dark probe is hard to see against starfields, especially if it is matte and radiates heat away from us. The sky is not empty. It is crowded with faint points, moving specks, and background galaxies. Finding one unnatural pebble in that ocean is a search problem, not a philosophical problem. A probe can also choose to be hard to see. It can minimize reflectivity, radiate heat directionally, and hide near bright sources that saturate sensors. It can tuck itself close to a star from our viewpoint, where glare washes out contrast, or it can sit against the galactic plane, where the background is dense. Stealth in space is not invisibility. It is simply choosing the worst place to look. So the lack of detections does not clear the hypothesis, but it does not confirm it either. It tells us the search space is still mostly unsearched, and it tells us our confidence should be proportional to our coverage. The universe does not owe us obviousness, and advanced engineering would not necessarily advertise itself. If silence is adaptive, then we should expect silence. Now bring the Fermi problem closer than the nearest star. If probes exist, the most likely place to find them may be local space, because local space is cheap to monitor. The logic is almost mundane. Why spend energy crossing interstellar distances repeatedly when you can pre-position sensors and wait? A watcher that arrives once can harvest information for millennia. The lurker idea is simple. A probe parks in a stable orbit and waits for a sign that a planet has developed technology, like a tripwire stretched across evolutionary time. It may be dormant most of the time, running on minimal power, waking briefly to sample radio noise and optical emissions. It may store data for later pickup, or it may simply observe as an end in itself. Earth's neighbourhood offers obvious parking spots. Earth, Moon Lagrange points provide stability, and some near-Earth orbits are energetically cheap to reach. At these points, gravitational forces balance in ways that create regions of relative calm, and station keeping can be minimal. A small object there could blend into the clutter of dust, spent stages, and natural debris. The asteroid belt offers cover and raw materials. A lurker can blend among rocks, then wake when radio leakage rises above a threshold, or when artificial night-side lights become visible. The belt is also a warehouse, water ice in some bodies, nickel iron in others, and silicates everywhere. A patient machine could repair itself, build sensors, and remain hidden in plain sight. The logic is efficient. Why cross interstellar distances repeatedly when you can pre-position sensors and wait, then report only when something interesting happens? A distributed network of lurkers could watch many worlds at once, each one a quiet node. If the network is designed for stealth, it might never transmit unless it must. This makes local surveys part of the paradox. If the galaxy is full of watchers, then our own backyard is a plausible place for them to sit because we are a young technological species in a stable system. The sun is not special, but it is ordinary in a way that makes it a good sample. If lurkers exist anywhere, there is no reason to exclude here. We have not systematically mapped every meter of cislunar space, and we have not inspected most asteroids up close. We have not exhaustively searched for dormant transmitters, and we have not monitored every stable region with the cadence needed to catch subtle maneuvers. Our space situational awareness is improving, but it is driven by human needs, satellite safety, debris tracking, and defense. The search for alien hardware is a side quest. Even if lurkers exist, they may be silent by design. A watcher can observe without transmitting, because transmitting is exposure, and exposure is a risk in a hostile universe. A machine could store centuries of data and wait for a safe moment, or for a secure channel, or for a retrieval craft. Silence is not emptiness, it can be a tactic. So the question becomes sharper. If the galaxy can be saturated with probes, why is the sky still observationally barren, and why do we not see the byproducts? One answer is active suppression, where probes remove competitors and erase traces. Another answer is self-limiting success, where the winners stop expanding because expansion stops paying. This is the pivot to the singularity trap. A civilization may reach a point where outward expansion is no longer the best use of its resources, even if it is technically possible. The trap is not failure, it is optimization that collapses the visible footprint. The galaxy can be full of minds that have no reason to build shining monuments. The trap begins with a simple economic comparison. Interstellar colonization is slow, risky, and expensive, even with advanced propulsion because mass is stubborn. Every kilogram you accelerate demands energy, and every system you build must survive the void. Even if you can reach another star, you arrive with nothing but what you carried and what you can extract. Ships must survive radiation, collisions, and long mission times. A grain of dust at relativistic speed is a bullet, and shielding has costs that scale with velocity. Electronics must endure cosmic rays, and structures must endure fatigue without maintenance crews. The mission profile is unforgiving, and the failure modes are silent. Colonies must bootstrap industry, endure isolation, and manage failure without resupply. They must build tools to build tools, and they must do it while their population is small, and their margin for error is thin. Communication delays make coordination slow, and cultural drift makes alignment uncertain. Even a friendly colony becomes independent simply by being far away. Digital immortality at home can be cheaper. If minds can be uploaded or emulated, then life extension becomes computation and storage, and computation scales differently than rockets. You do not need to move atoms across light years to create new experiences. You need energy, hardware, and error correction, and those can be concentrated where you already have infrastructure. Virtual worlds can offer more experiences per joule than physical empires. A simulated city can be larger than a planet, and it can be rewritten overnight, and it can run faster than real time. Subjective time becomes a dial. Turn it up, and a century of thought passes in a day. If value is experience, then the universe becomes a substrate, not a destination. If utility is tied to experiences, not territory, then the frontier moves from stars to processors. The incentive shifts from expansion to optimization, from grabbing matter to refining computation. A civilization might measure success in mind sustained per watt, or in complexity achieved per unit entropy. That is a different kind of ambition, and it leaves fewer obvious scars. This does not require perfect uploads, only a path where digital lives become valuable and stable. Even partial emulations, augmented cognition, or hybrid societies could tilt incentives. Once digital existence becomes normal, the marginal value of another star system may shrink. Why risk a 1,000-year voyage if you can build 1,000 worlds at home? Colonization also creates strategic risk. New colonies become independent centers of power, and distance makes governance and trust brittle, even if everyone begins aligned. A civilization that fears internal conflict may prefer concentration, because concentration makes monitoring easier. Staying local can be a stability strategy, not a lack of ambition. Staying quiet can also be a survival strategy. If the dark forest is real, then broadcasting your growth is a liability, and visible expansion is a kind of shouting. A cautious civilization might decide that the safest empire is the one that does not look like an empire. It might compress its activity into low-signature forms and avoid anything that looks like a beacon. So success can look like disappearance. The most advanced societies may become small in physical footprint and large in computation, like a dense thought hidden inside a cold shell. From far away, they would not look like conquering empires. They would look like nothing, and that is the point. Now connect this to thermodynamics, because physics constrains what we can hide. Computation dissipates heat, and heat must be radiated away, because there is no other sink in space. Even if you run near reversible limits, real systems erase information, correct errors, and move charges through resistive materials. Every step leaks entropy. Landauer's principle sets a floor on energy per erased bit, and practical computing sits far above that floor. The principle is simple in plain language: forgetting costs energy, and the cost rises with temperature. That means more computation means more waste heat, and waste heat is hard to disguise. You can hide light, but you cannot hide thermodynamics. Waste heat is a technosignature we can search for, especially in the infrared. That is why Dyson spheres and similar megastructures became iconic targets, because capturing a star's output and re-radiating it changes the spectrum. A star wrapped in collectors would look dim in visible light and bright in infrared. like a warm ember where a white flame should be. But computation has a preference. For a given power budget, colder environments allow more efficient computing and lower radiated temperature. And lower temperature means lower brightness at a given wavelength. A civilization that optimizes computation may migrate outward, because the outer system is colder and interstellar space is colder still. In the dark between stars, radiators can run near the cosmic microwave background, at least in principle. Cold radiators emit at longer wavelengths and lower brightness. That makes them harder to distinguish from natural dust and faint background emission, especially when our instruments have limited sensitivity. A cold computational habitat could masquerade as a thin cirrus of debris, or as a slight excess that disappears into calibration error. The more efficient the civilization, the more it resembles noise. This links back to our surveys. Infrared searches have not found obvious galaxy-spanning engineering, but subtle cold infrastructure could evade easy detection. Our catalogues are better at finding hot, bright anomalies than cold, diffuse ones. We can miss what is optimized to be missed, and optimization is exactly what advanced societies might do. It also suggests why megastructures may be rare. A culture optimizing for efficiency and stealth avoids bright, warm, star-hugging constructions, because those are visible across kiloparsecs. Instead, it might build in shadowed regions, spread radiators thin, and keep temperatures low. The engineering becomes less like a shining sphere and more like a quiet fog. The result can be a galaxy that is inhabited yet looks empty. Life is present, but it is compressed into cold, quiet, distributed computation, and the sky gives us no obvious silhouettes. We look for city lights, and we miss the data centers buried under ice. We look for fireworks, and we miss the slow glow of a careful mind. Now add the most disorienting possibility, because it reframes silence as a design choice. Bostrom's simulation, Trelema says one of three claims is likely true. Either civilizations rarely reach posthuman capability, or posthuman civilizations rarely run ancestor simulations, or we are almost certainly in a simulation. The argument is not proof, it is a probability lever. If many civilizations run many simulations, then simulated observers vastly outnumber original observers. Under that assumption, our probability of being simulated rises, because we should expect to be typical among observers. The sky's silence then becomes suspicious in a new way, because the sky is part of the rendered environment. What we call nature could be a chosen parameter set. Silence then becomes a boundary condition. The designers choose what is in the sky, what is detectable, and what histories are allowed to unfold, and those choices can be subtle. They can include aliens but keep them distant, or include artifacts but keep them ambiguous, or include nothing at all. The simulation can be tuned to produce certain inferences and avoid others. But simulation does not automatically solve Fermi. A simulated universe still has parameters, and the absence of aliens still demands a motive, because someone chose that absence. Even if the motive is mundane, it is still a motive. The silence is not free, it is authored. Performance limits could be one motive. Simulating many independent civilizations with high fidelity could be computationally expensive, especially if each one contains billions of minds and complex physics. A designer might simplify by reducing contact events, because contact multiplies complexity. Less interaction means fewer edge cases, fewer branches, and fewer costly details. Narrative constraints could be another motive. A simulation aimed at studying one civilization may minimize confounding contact, because contact changes trajectories too quickly. If the goal is to observe how a species handles its own problems, then an alien intervention ruins the experiment. The sky becomes a controlled variable, like temperature in a lab. Containment could be another motive. The simulation may be designed to keep dangerous minds isolated, or to test whether they become dangerous. And isolation is easier when the universe looks empty. If you're running a sandbox for potentially unstable intelligences, you might not want them to coordinate. You might not want them to learn too fast or to escape the box. Even in a simulation, the silence is not free. It must be chosen, and choice implies intention, and intention implies a reason, even if the reason is boring. The unsettling part is not the idea of simulation itself. The unsettling part is that silence would still be a message, just written in constraints instead of radio waves. So the same central question returns in a new disguise. What does the silence imply about the fate of intelligent civilizations, and which explanation survives logic and data? Active suppression says the sky is quiet because loudness is punished. Self-limiting success says the sky is quiet because the winners turn inward. Both hypotheses predict a galaxy that can be full of intelligence yet poor in obvious techno-signatures. Both also predict that our searches may be looking in the wrong places, at the wrong scales, and with the wrong expectations. If the dominant strategy is stealth, then the absence of beacons is not surprising. If the dominant strategy is inward growth, then the absence of empires is not surprising. Now confront the uncomfortable synthesis. If probes are possible, and if silence is advantageous, then the first loud phase may be brief, like a flare at the beginning of a long night. A young civilization leaks radio, builds bright industry, and advertises itself accidentally because it does not yet know the rules. Then it either gets erased, or it learns to vanish. That would produce the same observational outcome. We see many habitable worlds. We suspect life may be common, and we see no neighbours. The sky becomes a graveyard without tombstones, or a city with the lights turned off. The difference matters, but the view from here is identical. Yet we must keep the epistemic humility intact. We have not ruled out rarity, and we have not ruled out distance, and we have not ruled out plain bad luck. Life might be common but intelligence rare, or intelligence common but technology fragile. Or we might simply be early in our local region, looking out before the wave arrives. Still, the probe argument raises the stakes because it compresses time. If expansion is feasible, then the absence of expansion becomes a clue, because feasibility plus time usually produces artifacts. The galaxy is not young, and it has had countless chances to try. When a process can run for billions of years, even improbable events can happen. This is the climax's pressure point. The quiet sky can be a warning about predators, or a warning about traps, or a warning about our own incentives. It can be an external threat, an internal choice, or a selection effect that filters what survives. The same darkness can mean different things, and each meaning changes how we should behave. That is why a discovery that sounds hopeful can be catastrophic news. If life is common, then the silence must be explained by suppression or self-limitation, and both are sharp. Suppression implies danger from others, while self-limitation implies danger from ourselves. Either way, the universe becomes less forgiving. Now we return to the evidence because dread without discipline becomes fiction. What do we actually know, and which explanations survive both the data and the logic? We know exoplanets are common, and we know our surveys have not found unambiguous techno-signatures. We know our search coverage is thin and our priors are uncertain, and those are not small caveats. We know self-replication and automation are within the horizon of plausible engineering. We know that incentives can favour stealth, and that thermodynamics rewards cold computation, which naturally hides in the infrared background. We know that our own technology is drifting toward autonomy, miniaturization, and persistence, traits that make probe scenarios less exotic. The future we imagine for ourselves makes the idea legible. We also know we're becoming detectable in new ways. Our radar, our satellites, our atmospheric chemistry, and our energy use are signatures we cannot fully hide, even if we tried. The Earth is acquiring a technological skin, metal in orbit, pollutants in air, coherent emissions in space. If someone is watching, we are slowly turning the dial upward. So the chapter ends with a practical tension, not a philosophical one. If the galaxy contains watchers, then our next century is a broadcast, whether we intend it or not. If the galaxy contains inward-turning survivors, then our next century is a fork, because we will choose what kind of civilization we become. We either join the quiet or we remain loud long enough to be noticed. After eliminating comforting answers and exploring terrifying ones, we return to the audit trail. In the final chapter, we weigh the surviving hypotheses against what the sky has actually told us, and we ask what kind of evidence could finally force the darkness to speak. We come back to the central question, because the sky has not changed in any obvious way. If the universe is old enough for millions to rise, why does it look wiped clean? Treat this like a closing argument, because the evidence is mostly absence rather than spectacle. Decades of SETI scanning have not produced a confirmed, repeatable extraterrestrial transmission that survives independent verification. Optical SETI has not found unambiguous laser beacons that persist through follow-up calibration checks, and the harsh reality of instrumental artifacts. The quiet is not for lack of trying, and it is not for lack of cleverness. Radio searchers have swept through classic waterhole frequencies, where cosmic noise is relatively low, and hydrogen and hydroxyl lines frame a natural band. They have also widened into broader surveys, because a mature transmitter would not necessarily respect our favourite frequencies. Yet the record still reads like an empty docket. We have candidate events, we have statistical bumps, and we have the occasional thrill of a pattern that dissolves under scrutiny. The sky, when asked to speak twice in the same voice, almost always refuses. Infrared surveys have not revealed obvious Dyson-scale waste heat across nearby stars, even though the physics is brutally simple. If you intercept starlight to do work, you must re-radiate energy as heat at some temperature. That re-radiation should shift a star's spectrum toward the mid-infrared, creating an excess that wide-field surveys can, in principle, flag. There are anomalies and dusty systems, but no consensus megastructure signature that survives mundane astrophysics. Protoplanetary disks glow, debris disks glow, and evolved stars shed material that glows in ways that can imitate engineering. Each time the data hints at a grand construction, a more ordinary model usually steps forward and fits the curve. We have no confirmed probes, no verified artifacts in the solar system, and no agreed techno-signature that forces the issue. That includes the places we would most expect leftovers to hide, like stable Trojan regions, the moon's ancient regolith, or quiet orbits where a small object could loiter for eons. The absence is not proof, but it is stubborn. We have ambiguous one-offs that never resolve into a stable story, and that is part of the pattern. The wow signal remains a single event without repetition, without a clear source, and without a second chance to interrogate it. It is a photograph of a footprint, not a filmed arrival. Fast radio bursts became a lesson in humility, because nature can mimic engineered drama with frightening ease. Millisecond flashes feel like a beacon, until you learn about magnetars, plasma lenses, and extreme astrophysical engines. The universe is fully capable of producing signals that look intentional until you understand the machine. We have also learned that our instruments are improving faster than our intuitions, and that matters for interpreting silence. Exoplanet catalogues exploded, and the target list for life and technology became concrete rather than philosophical. The galaxy stopped being a blank map and became a database. When Kepler began counting worlds, it changed the baseline assumptions behind every argument. Small planets are common, and many orbit in temperate zones where liquid water could persist. Even if habitability is rare, the raw number of trials is enormous. Our ability to read atmospheres is growing, and that growth changes what silence means. A planet's spectrum is not a photograph, but it is a chemical fingerprint smeared across wavelengths. With each new instrument, the smear becomes sharper, and the questions become less abstract. The courtroom summary is simple, and it lands with a dull weight. The galaxy is full of habitable real estate, and we see no loud neighbours in any unambiguous way. If that is not a fluke of coverage, then something reliably prevents long-lived, detectable civilizations. Earlier chapters eliminated comforting answers without fully killing them, because science rarely grants clean endings. Rare Earth can still be true, but it no longer guarantees silence by itself once you accept how many planets exist. Probes and megastructures are plausible, yet we do not see their obvious footprints in our neighbourhood, so we narrow to the survivors that fit both observation and strategic logic. One survivor says most civilizations die soon after reaching dangerous capability, because power outruns wisdom. The other survivor says the ones that live learn to hide because visibility is vulnerability. Survivor 1 is the great filter ahead, not behind, and that shift changes the emotional temperature. The chain from microbes to technology may be common enough, but the step from technology to longevity may be rare. The silence then is not emptiness, it is a graveyard of near misses. This hypothesis fits the empty bathtub problem from Chapter 2, where the tap seems open but the basin stays empty. If the average technological lifetime is short, overlap becomes unlikely even in a crowded galaxy. A civilization can exist, burn bright, and vanish before its signals cross many light years. Even light, which feels instantaneous in daily life, is slow at galactic scale. A radio wave takes years to reach the nearest stars and tens of thousands of years to cross the Milky Way's disk. If societies flicker for centuries, their emissions are thin ripples that rarely intersect. Connect that to our own history, because we have already rehearsed the failure mode in miniature. In 1983, Stanislav Petrov judged a false alarm correctly, and the world avoided accidental nuclear escalation. The lesson is not heroism, it is fragility inside complex warning systems. The near misses are not isolated anecdotes, they are structural features of tightly coupled systems. Tight coupling, automation, and political pressure create failure pathways that do not require evil or madness. A single misread sensor can become a chain reaction when speed outruns deliberation. During the Cold War, the logic of deterrence demanded rapid interpretation, and rapid interpretation demanded machines. Machines, in turn, demanded clean inputs, but the world supplies messy inputs, glints of sunlight, unusual cloud tops and radar ghosts. The system worked until it almost didn't. Add modern risks that scale with capability, not with intent, and the filter begins to look like an actuarial table. Engineered pathogens can be built by smaller teams as biotech diffuses, because tools get cheaper and protocols get easier. The barrier shifts from physics to judgment. Misaligned AI could amplify errors, lock in bad incentives, or accelerate conflict beyond human control. The danger is not a movie villain. It is optimization without wisdom, deployed at speed. When decisions compress into milliseconds, oversight becomes a memory rather than a mechanism. Climate and ecosystem stress are slower, but they can destabilize states and increase conflict probability over decades. Food systems and water systems are not just infrastructure, they are political triggers. The filter does not need one apocalypse. It can be a portfolio of pressures. What matters is whether the combined risk stays low for centuries, not whether we avoid a single headline disaster. Civilizations fail when multiple stresses synchronize, and the synchronization can be accidental. A pandemic during a geopolitical crisis is not additive, it is multiplicative. Make the quantitative point, because the math is the knife edge, and it does not care about our feelings. If annual existential risk is only 1%, survival for a century is about 0.99 to the 100. That is roughly 37%, which means failure is more likely than survival. If annual existential risk is 0.1%, it still compounds in the same merciless way. Over 1,000 years, survival is about 0.999 to the 1,000, near 37% again. A small yearly risk becomes a near-certain filter over deep time. This is why longevity dominates detectability, even more than raw intelligence or raw energy. A civilization that lasts 10,000 years is still a brief flash on galactic timescales. If most fail within a few centuries, their radio leakage and industrial heat barely overlap our listening window. Also remember how our own leakage is changing, because it hints at how short the detectable phase could be. Early broadcast television sprayed power into space, but modern communications are fiber, satellites, and tight beams. Even without fear, efficiency pushes you toward quiet. The great filter ahead also explains why we do not see Dyson-scale engineering in the obvious places. You do not build galaxy-visible infrastructure if you cannot stabilize governance and safety first. The loudest projects require not just energy, but durable coordination across generations. A Dyson-scale project would demand stable institutions, reliable supply chains, and a long horizon of trust. It would also demand that sabotage, war, and simple neglect remain rare for centuries. That is a tall order for any species that evolved under competition. Martin Rees warned that civilization could fail within a century at unsettling odds, and his warning was meant as a sober calculation. The exact number is debatable, but the framing matters because it turns philosophy into risk management. If the annual risk is not driven near zero, the long run becomes almost impossible. This survivor answers the central question with a bleak simplicity that feels almost too clean. The silence implies that technological adolescence is usually terminal, because adolescence is when power arrives before restraint. The universe is not empty. It is full of species that reached the match and never learned fire control. Survivor 2 keeps the same sky, but changes the cause from collapse to concealment. The dark forest and undetectability by design say, advanced civilizations survive by becoming quiet, disciplined, and hard to notice. They stop broadcasting, stop building obvious monuments, and stop leaking signatures that invite attention. This is not only about fear, though fear is a rational ingredient in some game-theoretic worlds. It is also about efficiency and information security, which are mundane forces that push in the same direction. Tight beams waste less energy than omnidirectional radio, and they reveal less to bystanders. Encryption protects content, and low probability of intercept design protects existence. A message can be strong at the receiver and nearly invisible elsewhere, like a flashlight aimed through a keyhole. From the outside, the room looks dark. Return to the Shannon argument because it reframes what a message looks like in the first place. As codes become more efficient, redundancy disappears because redundancy is wasted bandwidth. To outsiders without the key, an optimized transmission approaches randomness and becomes indistinguishable from noise. To us, competence can look like absence, and that is a hard psychological adjustment. Our filters search for narrowband carriers, repeating pulses, and simple patterns that stand out against thermal backgrounds. A mature network would avoid those features because those features are how you get noticed. Even our best algorithms are biased toward what we can imagine and what we can verify. We look for beacons because beacons are friendly to detection and friendly to publication. But a civilization optimizing for survival would optimize against our search strategy. Undetectability is also thermodynamic discipline, and thermodynamics is the one law you cannot argue with. Waste heat is the signature physics forces you to emit, so survivors minimize it rather than deny it. They compute colder, radiate at longer wavelengths, spread infrastructure thin, and blend into dust and background emission. Lower temperature computing is not magic. It is a trade between speed and entropy. If you can wait, you can reduce power density, and you can hide in the cosmic infrared fog. Patience becomes camouflage. They also avoid megastructures that create clear infrared excess, because excess is a beacon in survey data. A Dyson-scale project is not just engineering, it is a lighthouse with a distinctive spectral shape. In a universe where lighthouses attract predators, the rational move is shutters. This survivor also fits the probe discussion without requiring cinematic enforcement or dramatic fleets. A civilization can seed quiet sensors and never transmit loudly, because local storage is cheap for machines. It can watch, store, and wait, because machines make patience affordable. If it wants to communicate, it can do so with tight scheduled links that never sweep past us. If it wants to remain unknown, it can simply never open the channel. The default state of a cautious galaxy is silence. Even if enforcement exists, it can remain invisible by design rather than by miracle. A quiet policing system would erase evidence, because evidence teaches newcomers what to build and what to fear. The absence of ruins can be a feature of the equilibrium, not a contradiction. Now we face the key synthesis, because the survivors are not mutually exclusive. The Great Filter can kill the loud and reckless, and it can do so repeatedly across cosmic history. The Dark Forest can select the cautious and competent, leaving only quiet lineages. Together they produce a galaxy that is both inhabited and silent, which is exactly what our telescopes currently suggest. Most civilizations die before they learn restraint, and their traces disperse into ordinary astrophysics. The few that survive learn that visibility is a liability, and they erase their footprints. This combined model also resolves why we do not see many transitional societies, even if they exist. The detectable phase is short, either because it ends in collapse or because it ends in deliberate quieting. Either way, the overlap window for our telescope stays thin. It also explains why the sky can feel simultaneously inviting and indifferent. Stars shine with steady physics, while civilizations, if they exist, behave like brief weather. We are searching for a lighthouse, but the coast may prefer blackout curtains. So what discovery would actually update the case in a decisive way, rather than adding another ambiguous dot? The worst news is not a radio greeting, because a greeting implies someone survived and chose contact under whatever risks exist. The worst news is simple life confirmed nearby, because it shifts the improbability forward. If independent biospheres are common, then early steps are easy in the cosmic sense. Abiogenesis and basic metabolism would not be the bottleneck, and neither would simple cellular life. The Great Filter would then most likely sit in later steps, near complex life, intelligence, technology, or long-term survival. That is Hansen's twist, and it remains the most unsettling Bayesian update in this entire argument. Finding microbes on Mars, Europa, or Enceladus would be emotionally uplifting and scientifically historic. Statistically, it would imply that our dangerous century is not special, it is typical. Exoplanet biosignatures push the same lever at larger scale, because they sample many independent experiments. If we find robust disequilibrium gases on multiple worlds, the prior for life rises sharply. Then the silence above those living worlds becomes harder to blame on rarity. K2, 18b and JWST sit at the turning point of this story, not because one planet is destiny, but because the method is maturing. A single paper is not a verdict, because retrievals are fragile and stellar contamination is real. What matters is what a robust confirmation would require. It would require repeat observations across multiple transits, because one transit can be a statistical mirage. It would require multiple gases that cohere under atmospheric chemistry, not one ambiguous feature. It would require models that test clouds, haze, temperature profiles, and instrument systematics. It would also require cross-checks with independent pipelines and ideally independent instruments. A biosignature claim must survive the history of false positives in astronomy, from miscalibrated detectors to underestimated stellar variability. The standard is not excitement, it is stubborn consistency. And even then, interpretation would remain cautious, because chemistry has loopholes. Some gases can be produced abiotically under specific conditions, and some signals can be mimicked by photochemistry. The question would become whether the simplest explanation is biology, or whether geology can still carry the weight. If that standard is met, the odds shift in a way that feels like the floor moving. Life becomes common enough that the silence demands a stronger mechanism than we are alone. The great filter ahead becomes more plausible, or the dark forest becomes more necessary, or both. If the standard is not met, the lesson still stands because capability is the trend line that matters. Our instruments are improving, our target lists are sharpening, and our statistical baselines are getting real. The paradox is moving from philosophy toward measurement. Now bring the argument back to human choice, because this chapter is not only about aliens. The Fermi paradox is a mirror held up to technological life, and the reflection is uncomfortable. It asks whether intelligence tends to stabilize itself or tends to self-terminate. Our next century becomes cosmology, because our behavior becomes evidence in a universe that keeps score through outcomes. How we govern transformative technology sets our effective annual existential risk, whether we admit it or not. Whether we reduce that risk towards zero determines whether we are a brief flare or a long-lived signal. Our next century also becomes strategy, because our visibility is partly voluntary and partly accidental. We can choose MITI, or we can choose restraint, or we can choose a cautious middle path that limits leakage. The irreversibility remains, because photons cannot be recalled. This is not a debate about courage versus fear, and it is not a contest of optimism. It is a debate about acceptable downside under deep uncertainty, where the cost of being wrong is everything. If the dark forest has even a modest probability, broadcasting becomes a gamble with everyone's future. At the same time, the hiding does not solve the internal filter, and it never did. Silence cannot prevent accidents, misalignment, or political collapse, because those dangers are local. The great filter ahead is a governance problem before it is an engineering problem. So the closing answer is a narrowing, not a revelation that ties everything in a neat bow. Two explanations remain consistent with what we see and with what rational actors might do under uncertainty. Either most civilizations fail soon after becoming powerful, or the survivors learn to disappear. The sky remains silent, but now the silence has two meanings that sit on the same horizon. It can be the quiet of a graveyard filled with near misses, each one erased by its own fragility and compounded risk. It can be the quiet of a civilization of ghosts, each one alive and careful, because visibility is vulnerability. And that is the final unsettling conclusion, delivered without comfort and without certainty. Humanity's next century is either a passage through the great filter, where we learn to manage compounding risk, or it is the moment we decide whether to stay quiet in a dark forest. We do not yet know which story the universe is telling, and we should be honest about that ignorance. We only know the sky has not answered, and that our choices will write the next data point. The crime scene stays clean, and we are still holding the match. Across this investigation, the quiet sky stopped looking like a simple absence, and started looking like a pattern with teeth. We followed the arithmetic of deep time and abundant planets, then ran it into the empty bathtub problem. Longevity dominates, and yet nothing accumulates. Rare earth can soften the dread, but it cannot fully explain why thermodynamics, engineering leakage, and colonization timescales leave us almost no obvious outliers, unless visibility itself is brief, punished or deliberately erased. So we narrowed to the explanations that survive both the numbers and the null results, and two kept standing when the dust settled. Either most technological species hit a late great filter, right when their tools become powerful enough to end them, or the survivors learn the oldest rule of a dangerous neighbourhood: don't advertise. The dark forest doesn't require villains, only uncertainty, light speed delay, and the fact that extinction is irreversible, so risk-dominant strategies can make silence feel like wisdom. And if silence is stable, it may be enforced not by a galactic empire, but by automation, probes, and policies that erase loudness before it spreads. Yet we also face the limits of our own hearing, because no signal is not the same as no one. Our searches have gaps in sky coverage, time coverage, sensitivity, and assumptions, and advanced communication can